spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful. To your call once more we rally, alma mater, hear our praise. Where the Wabash spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew. Of the days we've spent with you, all hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew. Of the days we spent with you, all hail our own Purdue. spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we've spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, your call once more we rally, alma mater, hear our praise. Where the Wabash spreads its valley filled with joy, our voices raise. From the skies in swelling echoes come the cheers that tell the tale of your victories and your heroes. Hail Purdue, we sing all hail. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue. When in after years we're turning alma mater back to you, may our hearts with love be yearning for the scenes of old Purdue. Back among your pathways winding, let us seek what lies before. Fondest hopes and aims they're finding while we sing of days of yore. Hail, hail to old Purdue, all hail to our old gold and black. Hail, hail to old Purdue, our friendship may she never lack. Ever grateful, ever true, lest we raise our song anew of the days we spent with you. All hail our own Purdue.
I would argue to have single photon sources could really further contribute to photonics-based quantum circuitry. And yet another discovery we did in our group, it's modulators, all optical modulators based on silicon SPAT, single photon avalanche diode. So because modulator is a key ingredient, and with this particular approach, which we recently started to develop, we might actually be able to beat other modulators, at least in some aspects. Well, when we speak of this recent development in quantum, of course, applications are spectacular and very impressive, covering this broad range: quantum communication, sensing, and particularly quantum computation, which everybody is excited about. And as we heard here and know well, there are many different platforms people trying to use, ranging from trapped ions, photonics, of course, we mentioned, semiconductor qubits, and atomic arrays. We saw quite tremendous progress in the latter approach specifically. But photons do have certain advantages because photons are fast, and with photonics you have extremely broad bandwidths, 10 to the 15, and bandwidth is actually very important. Speed and bandwidth, that's what makes a difference, and therefore one could argue it could be the fastest approach and provide the largest bandwidth, which means you could process more information. The problem, although photons are kind of hard to couple to materials, so the challenge here is how to couple photons to matter. And the problem stems from the fact that the wavelength is much larger than the size of nanoscale components, whereas the size of a photon, which is the wavelength, is like 1 micron, so there is quite a significant mismatch. So if you would learn to, on demand, switch on and off coupling of photons to these nanoscaled photonic components, that's actually a challenge, but if you accomplish it, that could make a difference. And I would, speaking of these advantages which brought with photonics, I mentioned these couple applications which we are familiar with. One in the area of quantum communication. It's quite a spectacular progress realized through satellite, where they connected China with South Africa. It's 13,000 kilometers. It's really impressive. And of course, these simulators, which address one particular problem. In this case, of course, is by no means it's universal quantum computer. And in this case, it's bosonic sampling, which does the job within microsecond. And the fastest computer, classical computer, which is in Oak Ridge National Lab, it will take 10,000 years. So clearly, there is a big promise for photonics approach. So what is good about photons? That photons could be flying qubits. You could actually encode information into photons, and you could use different degrees of freedom, which includes the path, geometrical path. It includes, of course, polarization. Polarization could be used as one of these degrees of freedom. And in addition to this, time domain and also orbital angular momentum. Recently, there is lots of activities to use actually frequency encoding, and my late colleague Andy Weiner did a spectacular contribution in this field, and now Joe Lukins, his former student, pursuing this direction. Of course, the goal is to bring it on a chip, and as was pointed out in last talk, the progress here is tremendous, and the fact that PsiQuantum working with global foundries, that's what the way to go to foundries, that actually makes a difference. So you basically go from this huge setup to this tiny chip. And the good news here that in principle, all the ingredients are there. So you have all these switches, you have all these filters, couplers, that's all well developed in foundries, and characteristics are quite spectacular, as we just saw in the previous talk. I would argue the most important things are two ingredients: generation of single photons. That, I think, something where you could have quite significant progress, and detection. At this stage, I mean, detectors are good based on these superconducting nanowires, but the low temperature, in principle, it would be really nice to get eventually detectors operating at room temperature. That would be a game changer. All right, but why silicon nitride? It's, as was pointed out already, it's because losses are really the smallest. If you look at the loss, it could go as low as 0.1 dB per meter, which is really quite impressive. This material is transparent in extremely broad spectral range between 400 to 2.3 micron. And of course, it's the most compatible. Refractive index quite high, so meaning that high contrast. So all these ingredients explain why silicon nitride became a material of choice when it comes down to nanophotonics. So coming back to single photon sources, as of now, the dominant approach, which works nicely, is based on this nonlinear parametric down conversion, either spontaneous parametric down conversion, which is Chi2 process, or spontaneous four-wave mixing, which is Chi3 process. Both of them are nonlinear, so the probability depends on how strong is the pump. And it's probabilistic, and that's actually a problem because when it's probabilistic, to increase probability of process to happen, you, of course, could increase the power, the pump, but that requires more power, and it brings a little additional problems. And also, it increases the infrastructure, basically, because you detect these heralded photons, and you do these selections, which photons are actually suitable. As opposed to this, if you have single photon sources, in this case, you have deterministic process. Basically, every time you excite your two-level system, you get a spontaneous photon. So and it could operate at much lower energy. So that's instead of probabilistic, you have this deterministic source. And it's well known, but it's notoriously hard to get good single photon sources. I mean, there are some like in quantum dots, but then it's so hard to integrate them into your circuitry, placing thousands of quantum dots-based single photon sources. And indeed, it would be fantastically good if you would have these sources in silicon nitride itself. And so far, it was a challenge. So here you could see this approach pursued by leading companies such as SideQuantum, Xanadu, and others, where basically you would like to do these quantum simulations by employing photons. And one of attractive features about using photons is actually low error rate, which is one of the biggest problems. It could be like 5 orders of magnitude less than in material-based approaches for computation. So error rate in photonics could be much less. It's a big advantage. So typically this computation is based on so-called one-way quantum computing when the single photon coincidence measurements plays the role of gating. So, and then you do it dynamically in a continuous regime. So depending on what the results of your measurements, you change the conductivity of your waveguides by using electro-optical switches, and depending on the algorithm you just want to do, so and that's you control the phase of your switches. So and of course the whole performance depends on how many modes you could handle, how many single photon sources you could use. And what is our contribution? We discovered this. Single photon sources occurring in the silicon nitride, they're inherent, so intrinsic single photon sources in silicon nitride. And their properties is actually quite impressive. So let's look into this in more detail. But what was the challenge first? Why people didn't see it before? The thing is, it's well known that there is quite strong fluorescent background in silicon nitride. So then even if you would have single photon sources, it's hard to see them because of that background. So the challenge was to suppress that background. And as people who actually made this key contribution to the field, and Alex Saintchev led this project, he's here in the audience. So one thing to do to enable these single photon sources is actually to use nitrogen-enriched silicon nitride, not stoichiometric, but nitrogen-enriched. And then miraculously, the background goes away. So that's a very, very good news. But then you still need to create these emitters. And for that, we use rapid thermal annealing. So what happens in this case, we believe that because thermal expansion coefficients for silicon nitride and silica, which is a substrate for silicon nitride, are different, when you do this rapid annealing, you create strain. And strain eventually causes these single photon emitters. One way or another, but when you do this thing, switch from stoichiometric to nitrogen-enriched silicon nitride and do this thermal annealing, you start seeing these very bright emitters. So what the properties of these emitters, it's kind of summarized here. It's all room temperature, I should emphasize. So this is a quantum purity, single photon purity, and G2, which is autocorrelation function. For room temperature is quite good. It's 0.1, and that's what we routinely observe. So the brightness, the number of counts per second is actually quite amazing. It's among the brightest sources. It's 10 million counts per second. They are not at telecom. They are indivisible. But I would argue it's not necessarily bad news. In fact, doing all this photonic circuitry indivisible could be much easier. And only the final stage, when you send it to optical fiber, you could down convert it to telecom, whereas all the circuitry, all the operation could be done indivisible, and it's actually easier to do than the same thing at telecom. So in terms of the nature of these emitters, we did this low temperature study and simulations, DFT simulations in collaboration with a team from Technical University of Denmark. And it looks like if you compare our experimental results with their simulations, so the nature of these emitters is related to this substitution of atoms occurring at the interface between silicon nitride and silica. And specifically, atom of silicon is replaced by nitrogen, and atom of nitrogen is replaced with oxygen. And that occurs at the interface. So this is our working model for the nature of these emitters. All right, so what we did so far, we didn't use global foundry facilities, therefore it's perhaps not as spectacular and smooth. But we did successfully demonstrate coupling to a waveguide. But first and most importantly, we found a way how to deterministically create these emitters. And for that, we just would use these silicon nitride pillars. Why? Because when you do this rapid annealing, of course, strain you create would depend on the diameter of your pillar. And by choosing properly the diameter, which in our case was around 200 nanometers, you actually could accomplish situation when you do this rapid annealing, your yield approaches 100%. So basically, you create this one single photon emitter per pillar. It's ideally, we're not there yet, but it's already quite good. If you take arbitrarily choosing this, in this case, 55 pillars, then it turns out 67% of them do have single photon emitter. So if it would be random, like in most cases, you create these single photon emitters by using, for example, some ion bombarding or some thermal approaches, it's random, then it's controlled by Poisson. And the probability to get your emitter is around 30%. We already have at least twice of that, which indicates that this is the nature of this emitters is deterministic. So we really could improve, ideally, yield and bring it close to 100%. That's what we are trying to do. And of course, this pillar you could place on the waveguide, and we did demonstrate already coupling of single photon emitters to a motorwave waveguide. We would use this gradient first to couple to waveguide and then outcouple it and prove that indeed they are single photon emitters by measuring this autocorrelation function. You could also inverse design optimize the coupling of this single photon emitter to a waveguide by using this odd-shaped structure, which was actually found through this inverse design simulation. And then the coupling of this quantum emission to a waveguide becomes actually quite high. Well, now let me switch gear and say a few words about plasmonics, and I will explain why it might be very important for further development of these single photon sources. Because historically, these unique properties, unique enhancement of optical processes related to plasmonics were developed for random structures, which tend to have non-trivial morphology, geometry, fractal morphology, I'll show results actually which we did long ago for these plasmonic structures, and they have this fractal scale invariant morphology. So what is fractal? Fractals basically reproduces the structure of the whole on a progressively small scale. Either deterministically, like in this case of fern, you see the structure of the whole is repeated on this scale, then on this scale, and so on. Or statistically, on average, and that's the case for this aggregate of colloidal silver nanoparticles. And if you do some statistical analysis, you would see that this actually has fractal structure. Why it's important? Because it turns out that fractal morphology promotes localization of plasmon excitations. When you excite with light these silver nanoparticles, of course, electrons are displaced and start to oscillate, and it acts like a dipole moment because the size of particle is just 10 nanometers. But they're all connected, they couple to each other. You should have these plasmonic modes, collective modes. But because of the fractal morphology, these collective modes tend to be localized in extremely small areas. And we referred to them as hotspots at the time. And these hotspots now used for many surface-enhanced spectroscopies, like surface-enhanced Raman spectroscopy and many other spectroscopies. Clearly, if you have this local field much higher than the field of incident light, then you would have dramatically enhanced nonlinear optical responses. So the other thing interesting about this is that the properties of these materials depend not that much on what materials are used, but largely about the geometry. In that regard, I could argue that this work on random composites and fractals was a precursor to so popular now metamaterials, when you design and engineer properties by controlling geometry and shape. But let me come back to plasmonics and explain why I believe it could be very important for quantum photonics. So in general, with quantum photonics, as I already mentioned in the very beginning, the challenge is how to effectively couple light to these structures which are much smaller than the wavelengths. And the solution was suggested by Ed Purcell, and he was actually a graduate of our school, electrical engineering school here in Purdue. And so what he said, it makes perfect sense. So if you place your atom, your system, which is much smaller than the wavelengths, in a cavity, since light bounces between mirrors many times, effectively it increases the coupling of light to your qubit or to your atomic system. And the increase, which now is called Purcell factor, is proportional to the quality factor. The higher Q, the more times light would bounce between mirrors, and inversely proportional to V, where V is the volume where your electromagnetic mode is localized. And that's now absolutely common approach to control light-matter coupling. So the thing with dielectric cavities, which is largely used, is that quality factor could be extremely high. For example, if you use defect in the photonic crystal, so then quality could go up to 10 to the 8, actually, and the volume, of course, in this case is limited by the diffraction limit, by the wavelengths. So Purcell factor could be enormously high. But the thing to note here, the higher the quality factor, the slower the process. Right? The response, of course, is inversely proportional to quality factor. System takes a while before it actually responds to stimuli because of high quality factor. And therefore, the alternative approach is actually not to go for high Q, but to go to extremely small V. And that's exactly where plasmonics comes into the game. Quality factor for plasmonic resonance is relatively modest, 100, but that's again not necessarily a bad news, because if quality factor is 100, it means your system is broad, has a broad bandwidth, and very fast. So the response in this case would be roughly like a terahertz range, right? Because the central frequency is, let's say, 1,000 terahertz. So if quality factor is 100, you would get like 10 terahertz response. But the volume for plasmonic excitation could be extremely small. So basically, for example, if you use metallic particles and the gap in between, it could be as small as 5 nanometers. So if you compare 5 nanometers to the wavelength diffraction limit, it's like 100 times smaller. So you should raise it to power 3. So it's about million factor in principle you could get only on the fact that plasmonics enables so strong confinement. An additional 100 because quality factor of plasmonic resonance. So the point here in terms of the Purcell enhancement, ideally, theoretically, it can be the same. But if you're using plasmonic structure, the system operates very fast. You don't sacrifice the speed. And that might be the biggest advantage of photonics, the speed. When you compare with all other approaches, they're extremely slow. And speed, why it's important? Because it provides yet another way to preserve these unique quantum properties, quantum coherence, and to deal with the problem of decoherence. The common approach to deal with that problem is actually to use extremely low temperature and trapping atoms or ions so that your system almost doesn't interact with any environment. Of course, it works. It's a good approach, but it's costly and not easy to do. The complementary approach which plasmonic could offer is actually to speed up your process to the extent that it happens before the decoherence event occurs. So basically, my process would outpace the decoherence rate. For example, if I'm talking about single photon emission, if my photon would be emitted before decoherence happened, for example, due to coupling of phonons or whatever, then it would be immune to decoherence. That's the idea we proposed with my postdoc at the time, Semyon Bogdanov, who is now a professor in Urbana-Champaign, and actually it's used now by many groups. So the idea that plasmonics might be one of the most attractive applications is speeding up the process and potentially beating decoherence. Quantum decoherence or maybe other decoherence because it's quite a general idea. So I'll show our baby steps in that direction, which done by Artyom Krivobok, our student. In this case, results as of now maybe not as spectacular, but they certainly could be improved because this is extremely recent. We have not even written a paper yet on this. So what Artyom did, he used this bullseye dielectric antenna. So you see it's right here, which confines light just through conventional cavity effect. And in the middle, he would place this silver nanoparticle, which provide plasmonic enhancement. So in this case, it's a hybrid system. So you can have confinement coming from the dielectric cavity and also from plasmonic structures. So the simulation showed that, yes, you should get this quite significant enhancement. You could see these high local fields. And what was measured so far, again, it's very, very recent results. So it's the Purcell is around like 50, 49 to be precise. And G2 barely touches 0.5, which is kind of the value when we say this is truly a single photon source. But again, it could be much faster. So, I mean, general consideration is like this. So the rate with which photons emitted are given by the spontaneous rate, which is around nanosecond. It's just Einstein coefficient. And the decoherence rate, typically because of coupling to phonons, it's on the scale of picosecond. So we are talking about speed up 10, perhaps 1,000 or 10,000. So if the rate of emission of photons would beat the rate of decoherence, then it would be immune to decoherence. So, and that means that Purcell factor we need to accomplish around 10,000. We are not there yet. But as simulations show, it's certainly very, very much achievable. If you really make small distance between plasmonic structures and your emitter, that factor at the level of 10,000 certainly should be achievable. So that's what we are working now on. And if photons, single photons, emitted at the rate faster than decoherence rate, then they become indistinguishable because they are emitted under exactly the same condition. There is no any role of environment. And in indistinguishable photons are the ingredients, are the building bricks which you need to create these cluster states. There are certain protocols how to make out of indistinguishable photons photonic cluster states that could be used for quantonic simulation. So that's the direction we are trying to pursue. So the division actually for this kind of summarized here. You have here this circuitry with light sources. We probably would need to use these antennas, this Purcell speed up, so that our single photons, which we already have, very nice single photon sources in silicon nitride, hopefully would become indistinguishable because they would be emitted at the rate faster than the coherence rate. Then you do all the circuitry switching, redirecting, and for that actually there is already well-developed technology. And eventually you have this detectors which measure this single photon coincidence, do the single photon coincidence measurement. All right, so that's the first part about these single photon sources and what we are trying to do with them. And the second part is actually about switches. Switches are very important, and that's actually critical also for doing simulations. And that brings us to another discovery done by our postdoc, Demid Sychov, and it's kind of I was very much surprised why it was not done before. So it's based on this single photon avalanche diode, which is a well-known technology in silicon. And just by simply repurposing it, using it for a different purpose, we showed that indeed it could work as an optical modulator with quite spectacular properties. But let me first motivate why this all optical modulation is important. Because, well, modulator, of course, is something which controls functionality of any circuitry. And typically it's electronic, it's great, but it's relatively slow. We would like to do it faster. We would like to use light. So, but one of the ways to do this optical modulation is through this control of refractive index. You see you have this linear refractive index, but you also have nonlinear contribution, which is called optical Kerr effect. And this contribution is proportional to the intensity of light. So then with control beam, you could change the refractive index for your source, and then the way of doing modulation, which could be actually quite fast. I'm showing here some works in this direction. So, but if you look at this M2, this Kerr effect, which is given in this table taken from Bob Boyd's textbook, it's actually very small, which means it would require quite significant intensity to change the refractive index in a significant way. So, and that's a problem. We would like to do it with few photons, particularly if you would like to bring it to quantum photonic applications, so it has to be done at extremely low intensities. So, to be fair, there are approaches where people do it with single photons, and they are summarized here. There is something in common between all these approaches. They use cavities with extremely high quality factor, which means that they're extremely narrow banded. They operate at only one single wavelength, and most of them are, not all of them, but most of them are also low temperature. So it's like the big question whether it would be CMOS compatible, and we ideally would like to put it on a chip. So which brings us to this idea, and here you could see Demid, who is also here in the audience. It's based on this SPAD, single photon avalanche diode. Let me remind how it works. You have this PN junction. You reverse bias it to high voltage, so that when the electron is incident on this PN junction, it creates first electron, which goes from the valence to conduction band, and then that electron is accelerated because voltage is high to the extent that it creates another electron, and then these two electrons create two more electrons, and that's you have this avalanche, exponential increase in the number of electrons. It's called so-called Geiger mode. So with one photon, single photon, you create up to 1 million electrons in holes. And that's why that's how the single photon diode works. So, and the thing here to appreciate here, the time rise for this avalanche is actually very fast. It's 10 to 100 picosecond. There is also so-called dead time, when the time which is needed for your device to be restarted so that it would be able to detect next electron. But that's also quite fast. It's around 1 to 10 nanoseconds, which is still very, very fast. So then the idea is simple. Okay, if you with one photon create up to 1 million electrons in holes, then of course you should significantly change the refractive index. And as calculations show, this is just textbook formula, then with one photon, actually we change the refractive index by 0.1%, which is spectacularly high. One photon change the refractive index by 0.1%. And the thing here, it's a very broad band because silicon, this SPAD operates in between 400 nanometers to 1 micron. And of course, it's CMOS compatible and potentially could be very fast. So that's the idea, and to check it, we did this very simple-minded experiment. So you have this chopper, which simply rotates with this speed like 1 kilohertz and modulate this control beam. In the control beam, we roughly have less than 1 photon per pulse. And the rate with which these pulses go, it's like 5 megahertz in this case, but we varied that number. And then you send a probe beam at 1.5 micron. The control beam is divisible, in this case 520 nanometers. And then we detect this probe beam after reflection from this p-n junction. So, and we see the same modulation with the same frequency as this chopper. So clearly, that's because of the chopper, you modulate the properties of your p-n junction, basically by creating this electron and holes, by creating this avalanche, which is detected with the probe beam. But this is a typical scheme for optical modulation. With one optical beam, you modulate properties for another beam. And the difference is it's CMOS compatible, it's broadband, it's on a chip, and the effect is actually spectacularly strong. So we studied the dynamics. I would not go into details. If somebody is interested, I would be more than happy to discuss it. But some important thing is that there is what I've shown here is actually this modulation as a function of delay between palm and probe. There is a gap between minus 70 to plus 70 nanometers, and that's coincides with this dead time, which I mentioned above. There is very strong but slower response, which with the typical time scale 13 microsecond, which we measured by using low repetition rate. And that's related to thermal conductivity and charge transport. It's actually known effect for modulating refractive index in silicon, but in this case, it's dramatically enhanced because one photon creates up to 1 million electrons. So it's orders of magnitude stronger than the conventional effect because simply you create by far more charges with one single photon. And there is also much faster response, which is smaller than this one, but it's still quite huge when you compare against modulation accomplished with other devices. In this case, the rise and fall time is around nanosecond. So nanoscale and very fast modulation. So we measured this modulation effect as the function of power for this probe beam and the function of power for the palm beam. And by doing so, you could extract this value of N2. How strong is this nonlinearity which you create with this avalanche caused by a single photon? So in this N2 is actually orders of magnitude higher than anything which was in the table I showed you a while ago. Interestingly enough, this slow response and fast response actually have different signs, as was measured by detecting relative phase difference between reference and modulated beam, which indicates they have actually different nature. Not only different time scale, but also different physical nature. So to sum up this part, yes, by using SPAD, and we just took a SPAD from a shelf, as I will elaborate in a moment, that certainly could be dramatically improved by purposely designing and developing this type of structure for optical modulation. But we already obtained quite spectacular result, which is like 2% modulation with single photon intensity, which that response is somewhat slow, 13 microsecond, but there is also fast response on the scale of nanosecond, which it still has extremely high, also record high actually, nonlinear response. And again, the biggest advantage is CMOS compatible and broad bandwidth operation. What are the possibilities to further improve it? First is just to use a cavity, but with very modest quality factor, because we don't want to lose the speed. So if you take a cavity with a quality factor like 1500 in this case, so then if you use this change in refractive index 10 to the minus 3 caused by a single photon, then the change in the wavelengths in this case would be like 1.5 nanometers if you assume that the length of this structure is 0.8 micron. And if I compare it to the full width at half maximum for this quality factor, which is 0.6 nanometers, then it's actually roughly twice higher, which means in this case you would have full modulation, 100% with a single photon by simply adding this cavity with a relatively small quality factor. And in terms of the speed, the ultimate speed of this device, if you really purposely develop it for optical modulation, could be controlled by simply the time which it takes for electron to go through the area where your light beam is, which is limited by the diffraction limit. If you take typical wavelengths, let's say 1 micron, typical drift velocity, which is 10 to the 7 centimeters per second, so you would end up with 3 picosecond. So in principle, this system could operate at rates close to terahertz and provide 100% modulation at the intensities of single photon. So it looks very promising. If I put it in the table, comparing other approaches, such as this Rydberg blockade in cold atoms, EIT, electromagnetically induced transparency, all these well-known approaches. Some of them do have modulation depths close to 100%. Some of them also relatively fast, not all, but some of them. And we are, in terms of this characteristic, not necessarily there yet. But theoretically, we certainly could accomplish this 100% modulation and operate at picosecond time scale. But the big advantage is this is CMOS compatible, chip integrated, and broad bandwidth. So that seems to be quite promising approach to eventually develop these modulators. And a similar idea actually could be also applied to detectors. That's yet another thing we are working now on, and I mentioned that one could argue one of the biggest challenges for this quantum photonic circuitry is emitters, which we now have a very promising emitters in silicon nitride, and detectors. And this idea could be applied for detectors as well. Anyway, so let me sum up. So in this lecture, I covered a couple things which we think could be useful for integrated quantum photonic circuitry based on silicon platform. And those two are emitters, single photon emitters, which are quite good, bright, operate at room temperature. And this single photon optical modulation by using this avalanche enhanced nonlinear optical responses. So here is the team with some friends. Of course, I'm just giving talks, but these folks actually working hard. And so let me stop here, and I would be happy to take your questions.
I think we have a question.
So from the previous talk, it seemed like the most devastating error that the silicon photonics platform experiences is photonic loss. Is this a problem that you think can be addressed by national labs and academia, or is this just strictly an industry problem?
Well, in what I'm talking about, we are not addressing the problem of loss. We rely on what already exists. And the truth is, what the previous speaker showed, what they are doing with global foundries, losses are getting extremely, extremely small. So still a limiting factor. Still, that would cause this error problem. And I'm not saying it's not a problem. But let's think, putting it on a chip and using multi-billion-dollar industry which developed, exists, it's actually extremely promising because the level of roughness, the smoothness which we could accomplish, it's quite spectacular because it's decades and decades of foundries which was developed for electronics. Now they adjusted it for photonics, even though it is a key problem, I fully agree. But that's the area where the progress is quite spectacular, and hopefully this system could work. So in terms of closeness to industry, this is a very well-developed industry because of its close connection to CMOS-based electronics. So we just redid it for photonics, but of course there are very specific features such as single photon sources, single photon detectors, and that's what we are trying to address. It's a problem, but there is a good progress there.
Thank you.
Any other questions? Great. If not, then we'll just have a short break and we'll reconvene in about 20 minutes. Thank you. discussion for a second. We're going to reconvene in about 5 minutes, actually. There's been a small change in schedules, so yeah, just so you know. So Henry from JPM Chase will be speaking in about 5 minutes. Thank you, guys. Okay, everybody, we're going to reconvene for the next talk. Our next speaker is Henry Liu from JP Morgan Chase. Henry is a senior research associate at JP Morgan Chase, and his research interests are in classical simulation of quantum computation, quantum supremacy, and quantum cryptography. And he obtained his PhD in physics from the University of Chicago, advised by Dr. Yuri Alexeyev. Thank you so much, Henry.
Having me over here. So today, the topic of the talk is going to be certified randomness generation on a quantum computer. So we really are very excited about this recent new result on Nature that we have published last month on the 26th. So, fresh out of the press as well. So, hopefully everyone's interested in this topic. The reason why we really wanted to pursue this process of, trying to generate random numbers is that in some sense this is the first useful quantum computational task that is performed by quantum supremacy type of experiments where it used to be the case that when you do random circuit samplings, the results are completely useless solving a contrived problem, right? But then we are able to manage to figure out a framework of looking at the problem and then use them for generating cryptographically useful random numbers. So I would like to really thank all the colleagues on this paper as well as Quantinuum for providing a world-class high-fidelity quantum computer to enable us obtain these really great results. So just a brief introduction of who we are. We're at the Global Technology Applied Research Team at JP Morgan Chase, and a lot of what we do span a range of emerging technologies, and quantum computing is one of them. For the quantum computing efforts at our firm, the important two thrusts that we do is to first look at immediate near-term useful applications of quantum computing, and also some slightly more longer-term approaches as well. Now, as you can see, probably that what we did recently with the certified randomness generation would be precisely for the one of creating value right now. But let's now dive into the scientific discussion. There has been a long history of folks building a quantum computer and doing proofs of principles that, oh, quantum computer is capable of doing something that a classical computer cannot do. And these are, quantum supremacy experiments, and primarily built on some kind of sampling problems, and namely random circuit sampling. You create a useless random circuit, and then you try to measure bit strings out of them. They have been performed on superconducting quantum devices. And more recently, with the partnership with Quantinuum, we were able to do a similar experiment at much higher fidelity that also results in very, very hard to simulate quantum computing results. Now, the question is, what is the utility in doing something like this? It used to be the case that it's good enough for you to say, this is a proof of principle that quantum is very capable, but not anymore, right? We now want more interesting story out of this. So it turns out that generating random number is a very interesting task for this problem because there are actually a lot of flaws with the way in which current random numbers are. For certain applications, maybe it's not good enough. So have an overview of a little bit of how we normally do random number generation today. When you have a classical computer, what you do is to source randomness from maybe CPU jitter or your mouse movement, and then that can be sent to a pseudo-random number generator, which is a deterministic mathematical function that is hard to invert. So an adversary seeing what the output is cannot know what the input was unless it spends a lot of computational power. So then you can essentially use this one-way mathematical deterministic function to stretch out your initial randomness and then keep on giving unpredictable output. As a result, these random numbers can be used for password generation and whatever application you have downstream. But you would run into a problem if your source itself is compromised somehow. And then the first way in which you can be compromised is that the hardware source of randomness you use is compromised. For example, you could purchase equipment from a malicious party who, instead of actually sample the randomness honestly, it will do this ahead of time, store all the results, and then replay it when they sell the hardware security module to you. And then your cryptography completely breaks down if the manufacturer colludes with some kind of hacker. Another possible problem is these supposedly secure pseudo-random number generators. These mathematical functions might actually be invertible if a malicious party planted some kind of secret. And in fact, the Edward Snowden revelation shows that a very famous and commonly used pseudo-random number generator was embedded a backdoor to enable the US government to invert this random function. So this is not a trivial concern. Another situation in which certified randomness may be interesting is when the random numbers used have to be shared among multiple parties that don't trust each other, and the random number has to be ensured to be fairly generated. So imagine a situation where you're playing a board game with your friend over the telephone, and then you need to roll dice. So like if you just simply tell, okay, you do it, then you realize they do a 6 every time, so they can cheat. So you need some mechanism of checking that these random numbers are honestly generated. And this is especially important for settings such as blockchains. We know Ethereum is starting to build proof of stake based blockchain services which require random selection of these verifiers. And you have these lotteries as well, and then some cryptographic protocols such as non-interactive zero-knowledge proof, which I will not explain right now, might also require shared randomness among non-trusting parties. So how you do this, really is a question that, is what we're trying to answer here. And then namely, we will use a quantum computer to perform a hard sampling task. Now, if the sampling task is only possible to do on the quantum computer, that means it's impossible to do it classically, which is a deterministic process, right? So it should be the case that if you can prove that these samples come from a quantum computer instead of a classical process, then you should be fairly confident that they are actually randomly generated. And to just go back a little bit, what is the sampling task? So for folks that are not familiar with the random circuit sampling, what you do is you initialize your qubit to the 0 states, and then you have random 2-qubit gates, random single qubit gates. So you create some state that is very close to hard random at the end, and then you project them to the computational basis. That gives you 1 bit string. And then you do this many, many times to get a bunch of samples. In order to verify that these samples actually do come from the quantum computer, what you do is to compute the so-called cross-entropy benchmark score, which is what we call the XEB score. They are an average of the probabilities for all of the bit strings. And the probabilities are, what is the probability of obtaining the bit string from that quantum circuit? So if it is from a quantum computer, then these probabilities on average should be high. So your XEB score should be high. Whereas if the bit strings are classically obtained, then they don't really have much correlation with the actual quantum distribution, because that's hard to do. Then the XEB score should be low. So the protocol to prove that the samples come from a quantumness require the consumer of the randomness to interact with the remote quantum server. What it do is to generate these random circuits, and then for each circuit, the quantum computer will return 1 string, and then it will return really quickly, really fast. And then, what the random consumer will do is to send part of the history, part of the string samples to a supercomputer that computes this XEB score. Now, why we need a supercomputer is because, these probabilities of getting the quantum samples, that's simulating the quantum computer, right? That should be hard. That is exponentially hard. So you need a supercomputer to do that. And in order for this process to be secure, it has to be the case that only a quantum computer is fast enough to return high-quality samples. So the amount of time that the quantum computer can take must be really small, whereas if this was classical, it should be long. So we can say something called the t-spoof as the time that a classical computer would take to spoof the process. That would be proportional to the fidelity of the quantum computer, turns out, and also proportional to how hard it is to validate on the classical computer side. So, this turns out boils down to a security requirement that if you have high fidelity and you have, strong validation resources and also very fast quantum computer, then your protocol is secure. Then you can show that the computer that gives you samples fast enough and gives you high quality output must be quantum samples. So far doing this has been very challenging because of these requirements, but until now, we're just able to perform this experiment. Overall, we are able to execute 30,000 quantum circuits and then select 15,000 of them to compute the XEB score for verification. And concretely speaking, in terms of the security requirement, we have fidelity of 30%. Validation of 1 circuit on the most powerful supercomputer roughly takes 100 seconds, and the quantum time is 2 seconds. So we have this more than 10-time gap between the spoofing requirement time and the quantum computer time. And as a result, we're able to extract 70,000 bits, and the security is that the probability that it could be spoofed by an adversary with 4 times the most powerful supercomputer is only 10 to the negative 6. And another important feature of our protocol is that we only do 1 sample per circuit. And this is because it turns out that if you want to sample 1 million samples from a circuit is actually much easier to classically simulate. So you can compare that with changing the circuits versus fixed circuit. Simulation cost is actually much lower. So what motivated our work was Scott Aronson and Shihan Han's 2023 stock paper that proved that for any kind of quantum or classical computer that takes your quantum circuit and then output K samples, as long as it passed the XCB test, then it must have linear entropy in N. So that's the complexity theoretic result that inspired our work. But because of the 1 circuit per sample setting, this is slightly different from their proposal, so we have to generalize our theorem to the 1 sample per circuit setting. But these kind of asymptotic analysis don't give you concrete numbers. For example, the entropy is proportional to omega n, but we don't know what the constants should be. So how do you get the concrete number? And also asymptotic theories assume that classical simulation is impossible, right? Because it's thinking about asymptotic limit of large number of qubits, whereas we know that if you want to do an actual finite size experiment, you have to make the circuits not too hard. Otherwise, the validation part on your supercomputer is also impossible. So classical simulation has to be non-negligibly, possible. So how do you incorporate this into your adversarial analysis? So we have to consider a fairly limited but also very realistic adversary that does this very simple thing. It either sends the sample to a classical simulation or sends to the quantum computer and perform actual sampling. Now, this is because we don't really know how else to obtain samples on a quantum computer other than to actually run the quantum circuit I got. There's no some sort of fault-tolerant algorithm that is known to scientists nowadays that spits out high probability bit strings without actually performing sampling. So these represent the state-of-the-art best techniques we know to spoof the XCB score. Now what the adversary would try to do is to do as few quantum samples as possible, because the classical ones don't give you any entropy. But the problem is that the classical samples will have low fidelity, so the XCB score will be low. So it will just try to give you as few quantum samples as possible while doing well on the XCB test. And in fact, with this adversary, you can analytically derive what the adversary's probability distribution of the score should be. So for each classical sample that has low fidelity, you can have an analytic derivation of the probability distribution of this transition amplitude, which is summed in the XCB score. And then for the high fidelity quantum sample, you can have a better probability distribution. Now, sum of the random variables distribution, which is the XCB score, you can also derive that as well. So you would have probability distribution of XCB scores for different cases, from all classical to all quantum and everything in between. You can see the probability shifts to the right of achieving on average higher XCB score as you put more and more quantum samples in it. So now the user of the randomness can say, I can tolerate, let's say, 5% threat. Then if I set my XCB threshold here, then I will be able to say, well, it at least has this much entropy without violating my security risk tolerance. So then, now that you have a lower bound on Q, you can then quantify the entropy. Now, for the verification part, which requires computation of these transition probability amplitudes, they turn out to be a contraction of a tensor network, which you can do on a supercomputer very easily, and this is very scalable onto the world's most powerful supercomputers. In particular, we used at the time the number 1, number 9, number 14, and number 30 most powerful supercomputers in the world, and we're able to obtain high numerical efficiency as well as 1.1 times 10 to the 18 floating point operations per second. Now this is roughly like 10 to the 6, 10 to the 5 times more powerful than your laptop, even a gaming laptop. So we're talking about really, really high performance supercomputing here for verification. So in summary, we did something that is from quantum supremacy that is in principle useful for cryptography. And if you want to read more details, you can see our Nature paper. So the second part, I would like to talk a little bit about applications. So far I've talked about how to generate these randomness, but exactly what are they useful for? Why is it not good enough for me to say I just use np.random. Like for Monte Carlo simulations, it's perfectly fine because I don't have any problem nowadays when I do my Monte Carlo simulations. It is actually, some cryptographic situations where you have to be extra paranoid. This is when it matters. So in order to see how this comes through, let's go through 4 properties of certified randomness that really make it useful. The first one is everlasting security, namely that your security assumptions only need to hold at the time of the protocol. If it gets broken later down the road, your randomness is still secure. This is unlike pseudorandomness. If at the time of generating your password, your pseudorandomness is secure, but then later on somebody discovered an algorithm that breaks like Shor's algorithm that breaks integer factoring, then they can recover your password, right? This is why you can say Bitcoin maybe later will have a problem, like, well, the Bitcoin that's stored in old wallets that are not secure could become stolen. The second one is classical remote verification. This is anybody who is getting these random numbers by interacting with a quantum computer on the cloud, on the internet, right? They can verify. This is in contrast to, for example, Bell test-based experiments where you're trying to do these randomized Bell basis measurement. That situation, you have to ensure that the measurement devices are not communicating with each other, and you cannot really check that without having physical possession of the device of some sort. So if you're just doing this remotely over the internet, you cannot actually verify the randomness. The third one is randomness expansion, where you take some input randomness that is short and your output is longer. The third one is amplification, where the input randomness that is consumed by the protocol is imperfect. Say, for example, if you have n bits, instead of n bits of entropy, you have n minus 3 bits of randomness. Just like instead of perfectly uniform, it's a little bit biased. But then your output is perfect. So let's now see why they're useful. But before we do that, overall, the high-level schematic of certified randomness is for the consumer to generate some input randomness, send it to the quantum prover, which sends a random response. Then you do some verification, and if it passes, you will then use a seed, combine that with the output to do a randomness extraction to take that imperfect randomness and make it perfect. So one application is so-called immunization of pseudorandom numbers. So for example, when you have a pseudorandom number seed going through a generator and then go to the output is seen by an adversary, what the adversary could do in principle is to either spend exponentially long amount of time to invert your pseudorandom function and then get your seed, which then allows the adversary to learn all the other pseudorandom number that you generated, or it could build in a backdoor into the pseudorandom number generator, which then allows it to crack your security without using exponential time. But if you go through a quantum process doing certified randomness, then the output is exactly perfectly random, right? There's no way for the adversary to invert a non-deterministic quantum process to get the seed of in any sense. So this is secure whenever the quantum computer is not colluding with the adversary, or that the quantum computer does not know the backdoor. Another application is differential privacy. So let me just introduce that concept a little bit. So say, for example, you have customer data stored in banks or hospitals, and then you have a data set that allows scholars or people to query what is the average age, what is the average height of folks, but you don't want it to be structured in such a way that anybody can learn an individual's height and individual's age. Right? You need to have anonymity, you have to give privacy. Hence the differential part, the differential part means you cannot single out any individual. Now, what an adversary can do, if it's able to access the mean of any arbitrary subset of the population, is that it can simply query everybody and then query everybody except A. And then, taking the difference between the mean, you lose the privacy for that individual. So differential privacy adds pseudorandom numbers into the queried mean. So instead of giving the mean, it gives mean plus some sort of noise. then taking the difference doesn't really give you the data of A anymore. But you might have an issue if the adversary can learn the noise, which then, if it knows what the noise is, then you have a problem. But the noise is supposed to be hidden from the querying party. So how does an adversary learn the noise? Because once it learns one noise from the output of the pseudorandom number generator, then it could, in principle, invert everything. So what it could do is to contribute a known data value to the data set and then do differential query to reveal the value of the known contributed data point plus whatever noise that it received. That allows it to learn the noise, which then allows the pseudorandom number generator output to be learned and then inverted, and then all the security guarantees become no longer secure. Now, again, with the quantum computer filtering in the middle, you can avoid this kind of problem. A more interesting class of applications is, as I said earlier, in the board game setting, a jointly verification setting where you have multiple parties that don't trust each other. But as we said, certified randomness require these quantum circuits that are sent to the prover, right? These circuits have to be random. These circuits have to be unpredictable to the quantum computer. But if Alice doesn't trust Bob, and Bob wants to collude with the quantum computer, then Bob could try to bias the challenge quantum circuits so that the quantum computer can, cheat somehow. So Alice has to ensure that C is random. The challenge is random without Bob being able to bias it. And Bob has to be able to ensure that C is random without Alice being able to bias it. So it turns out that there exists this thing called the coin flipping protocol, where as long as Alice and Bob have some private randomness to themselves, they can engage in a protocol to obtain unbiasable shared output C. That can then be used to feed into a quantum computer to do your certified randomness and then get the output. Now the question would be, well, if Alice and Bob are already able to engage in this protocol to generate trusted, unbiasable shared randomness C, why do I need to do certified randomness through a quantum computer? Now, the reason would be that, so first, in the situation where randomness is a scarce resource, which it is, especially for cases like headless servers that don't have human input, right? Where does the randomness come from? It's a virtual machine that lives somewhere. Where does the randomness come from? So it's a rare resource. In that case, Alice and Bob is only able to agree on a small amount of randomness at the beginning, right? And then what certified randomness can do is this randomness expansion property that allows it to stretch it longer by polynomial factor. Now, if you can stretch out the randomness, then you can potentially do a lot of useful things if the length of the original shared randomness is not sufficient. So this allows you to do a lot of things like randomness beacon. So randomness beacon is, for example, a public service of broadcasting random numbers that everybody can use. But the problem is that if you don't trust whatever public service that is doing that, then how do you get around this problem? So with certified randomness, the goal is hopefully that maybe you have a weak beacon source and then you can uplift the security guarantees on this by performing a remotely verifiable certified randomness protocol. Another class of problems are like so-called non-interactive zero-knowledge proofs. These are cryptographic protocols in which one party tries to prove to another party, for example, that I know the authentication key to something without actually having to tell them what the key to the authentication problem is. So proving the statement, proving one statement without revealing anything in addition to the truthfulness of the statement itself. So in this situation, it turns out that having shared randomness is really a useful thing. And a lot of times, the size of the randomness that you want to use is very, very large. So the randomness expansion property of certified randomness can be really helpful here. And finally, you can have these blockchain applications like Ethereum, like whatever lottery, e-games, or smart contract type of applications. You can do that. And I think a final class of application of certified randomness is position verification. I think this is one thing that maybe folks who are more physicists would be interested in rather than cryptographers. So in this kind of situation, what you want to do is to verify that there is a quantum computer somewhere you say there is. So let's say I want to prove that I have a quantum computer in this building. Then you can do this with certified randomness. Now, you might ask, why do I want to know that there's a quantum computer living somewhere? The hope is maybe one day you can extend this to being able to say, proving that a message originated from somewhere. So then you can prove that, oh, the message come from my office, so that has to have come from my boss. So I will do what the message tells me to do, right? Instead of some kind of eavesdropper that intercepted the communication and then pretend to be my boss to tell me to do something else, right? So in this protocol, what you can do is to have two verifiers at different locations around the location you're trying to prove that has a quantum computer. Each one verifier will send half of the quantum circuits to the prover, the quantum prover. And upon receiving both halves, the quantum prover will combine the two halves, and then, okay, now it knows the quantum circuit and is able to run the quantum circuit, sample it, and output the bit strings, which we will call answers. And then the verifiers on both sides will now compare if the answers they receive are the same answers. To see why this works for position verification, let's see how somebody might try to spoof it, right? Instead of being at the correct location, it has two different quantum computers at different locations. In this case, they receive each half of the challenge first, but then they can't do anything because it's missing the other half of the challenge. So what they would do is to forward the rest half to each other. Then after you've successfully forwarded, each party can now compute the entirety of the challenge, right, by some sort of combination. So now it knows the quantum circuits you want it to sample from, and now the first prover on the left side will be able to run the certified randomness, will be able to sample from the quantum circuit and then give the answer to the left verifier. And the right prover will do the same thing independently. It knows the challenge. It will try to do the sampling problem and then feed the answer to the other verifier. Now the answer prime is independently generated from answer, and then it's guaranteed that answer and answer prime must be different. Now the reason is we're doing a certified randomness protocol. So any answer that satisfies the challenge has to be random, right? There's no way for the two provers to, in general, get the same answer because the answer is guaranteed to be random. So you may ask the question, okay, why do they have to generate these numbers independently? Why do they have to sample from the quantum circuits independently, right? Can't let's say, the left person do the sampling problem first and then send the answer to the second one, and then the second one send the answer to the verifier, then the answers would agree. So this is because we put a timing requirement on when each of the verifier receives the answer. So it turns out that the speed has to be that with the speed of light, the challenge is sent here, and then the answer goes here, like continuously, just like nonstop. And the same thing goes here. Challenge goes here, and then answer gets here. So the requirement is that X and Y arrive to the prover at the same time, right? So this is the only way in which you can have a continuous stream of challenge and then answer traveling at the speed of light, nonstop, right? And in this situation, to make it a nonstop process, you have the answer you have the challenge go here, and then and then gets forwarded to this, right? And then immediately has to give the answer. It cannot really wait for anything. Otherwise, it'll take longer than it has to, and then the two verifiers are able to detect foul play. So this is how this allows position verification. So this is kind of the conclusion of this research effort, and I would like to acknowledge the Department of Energy for providing these really powerful supercomputers to allow us to do these validation problems. If you have any question, I'll be happy to answer, and thank you for having me here.
Great, any questions? Okay, awesome.
Yeah, it's a very interesting talk. I'm just curious, usually how many qubits are needed in these applications?
Right. So In this particular experiment, we used the 56-qubit quantum computer from Quantinuum. The qubit count itself is not really that important, right? So for applications, what you care about is the number of bits that you get in the end. So the qubit count will affect the number of total bits. But if it's too short, then you could sample more times, right, to make the bit string longer. Or if you don't need that many, you can sample fewer times. So you have some flexibility by sampling for more times or sampling fewer times to adjust the length of the randomness that you require. But there is a reason why you don't want to go to, let's say, 150 qubits, because as we mentioned earlier, verification needs a supercomputer, and if you have 150 qubits, then verification would be impossible anymore. So you can't go too much, but at the same time, you don't really want to go anywhere lower than 56 qubits anymore, because if you're significantly lower than that, then classical simulation to spoof you also becomes too easy. So you need to be in this sort of sweet spot of between 50 to 100 qubits for sure.
Thank you.
Could I ask a follow-up question on that? So how long did the classical computation take?
Right. So the particular circuit that we study would require 100 seconds to simulate on the most powerful supercomputer, which is, allows us to have this gap of tenfold between simulation and spoofing. Now, the actual amount of time it takes to execute on the quantum computer, which I didn't have the time to show, but now I realize that maybe I actually do have some time, is actually very short. So this part is actually only 0.8 seconds. But you have this huge compilation problem because we do the things over the internet, right? I tell Quantinuum what circuit to run, and it has to translate into pulse sequences, ion shuttlings, right? It takes some time. So it turns out that what we did is to amortize the fixed overheads by running compilations in parallel and then executing the circuits in sequences. But overall, yes, although you're able to bring down the average time per sample to 2 seconds, the physical time of actually running the circuit is only 0.8 seconds. It's even shorter. So as software improves, things will get even better.
It's a very interesting talk. I'm more on the physics side of these things, so the cryptographic schemes go a little bit over my head. But I have like a small question, like how do you generate those random circuits? Like, isn't the space of circuits very huge to sample from? And the second question, I don't know if you've mentioned it already, but what's like the state of the art like advantage of using quantum computer to generate random numbers versus like a classic protocol, like given the current noisy quantum hardware that we have? Mm-hmm. Thank you.
Yeah. So the first question was, wait, can I just a quick reminder?
How do you generate the...
Oh yeah, right. So let's go through the ensemble of the circuit. The circuit is, is a particular ansatz. For trapped ion devices, you can have, in principle, all-to-all connectivity by shuttling ions around. So what we do is, we will interleave SU2 single qubit gates with arbitrary pairs of n divided by 2 pairs of entangling gates, and these are CZ native, CZ maximally entangling gates. You don't need this swap part because then you can just permute and, it's trivial. So it's a sandwiching between CZ arbitrary pairs of CZ and also single qubit SU2 gates. Now, obviously, this set is not, really saturating hard random because then you need exponentially many parameters. So the argument is not really that I am producing actual hard random states. It is that I'm producing something that is sufficiently random that is, and then the way I do some theoretical analysis is to assume that they are hard random. But for the concrete problem of, okay, is it possible to simulate using an adversary? That you just benchmark your, classical simulation algorithms, and then you realize, well, in practice, it's not simulable, even if I'm not parameterizing the circuit with exponentially many parameters. So that's sort of the story here. Now, I think there's, of course, ways you could do this more carefully, like, for example, looking at the frame potential to see if it's approaching approximate T designs, whatever. But those things are computationally very intensive, and I don't think you can actually, you could use, existing constructions of pseudo-random unitaries, sure, and those are log depth, so they're not that bad. But I think for finite size, these constructions for pseudo-random unitaries are not practical for hardware, and also might actually be too hard to validate because they are Even though they're not that deep asymptotically, maybe finite size is still a little bit too deep to simulate.
I'm just curious, how robust are your validation models right now, validation protocols?
Sorry, could you repeat that?
How robust are your validation protocols right now,
How-
XCV scores?
What is the protocol?
Robust.
Robust, okay. So I think robustness comes down to two things that are important to say. Number one is the adversary model. In cryptography, you can prove any number you want. You can say I'm secure with probability 10 to negative 100, right, under certain security model. So the security model is a big part, right? How strong are you assuming your adversary to be? So right now, the adversary is assumed to do this simple thing of either classical or quantum, right? And then the quantum part is doing fair, honest sampling. So you could imagine that one day somebody come up with a quantum algorithm that tries to solve, sampling from random circuits without actually sampling it by running maybe Grover search to find the maximum probability bit string among exponentially many of them. So obviously Grover search is not efficient, but you can see, okay, maybe there are some algorithms you could do that. So in principle, you would need to be secure against more general quantum adversaries. So I think today it's more or less fine because everything is NISQ. Even if you come up with some kind of general quantum attack, it's still unlikely to be feasible in the near term. But this is sort of the question that the asymptotic analysis of Scott Aronson and Shihan Heng and our generalization tried to tackle. What if you don't assume that your quantum computer does that something specific, but then that does not allow you to get constants, concrete numbers of your protocol. So that's one aspect of the robustness, is that right now we're working with a little bit of limited adversary model, so maybe generalization will be good. And then the second aspect of security is the exact number that we get out. So being secure against 4 times as powerful as Frontier, the most powerful supercomputer in the world, with a probability of being spoofed by only, with only 10 to negative 6 is a pretty good parameter. So I think it's the more important weakness comes from the security model rather than the concrete numbers we derive from that security model. I'm sorry, I remember you had a second question. I don't think I actually got around to answering that. Okay. Right, what was,
the question was like, I think it's related, what's the state-of-art quantum advantage given the...
Oh, right, compared to classical approaches. I think classically you can do, for example, using lava lamps, right, using or thermal noise. So these things are genuinely random, but what you lack is the certifiability. You cannot verify. So then there's any kind of multi-party protocol, you might not be able to get the same kind of uplift as quantum.
These are some interesting results. It astounds me that you need thousands of, or I guess almost million GPU hours to achieve the 100 seconds per sample, but that makes me wonder, so I'm on the quantum software side, does the work here, I guess, depend on, or does the work here depend on the hardware not improving? Because one could imagine that the number of resources, the classical resources may go down somewhat in the future.
Yeah.
And also, as a parallel, considering that an adversary may not only have a cost and hardware budget, but they also have an energy budget, right? So then I'm wondering if there's any consideration given to the energy consumption between, say the quantum processors versus the classical processors.
Right. Thank you for the question. I think the gap is really, the important gap here is the verification cost, which is purely a classical process, and the spoofing cost, which for the adversary model we've mentioned is also a purely classical process. So for that part, your question I think was about is it possible to drive down the verification cost without having to have them run on supercomputers? And certainly it is, because let's say what you can do is you can decrease t-val if t-quantum becomes much smaller and still satisfy this inequality, right? So these are proportional. So if you can run, instead of 8-second latency, you can run 10 to the 6 many circuits per second, which you can with superconducting devices, or you can do that by parallelize your quantum computers. Then on average, you can also reduce by hundreds of thousands of times. Then you no longer need supercomputers. Maybe you just need a desktop PC. And then to the other question of quantum cost, I think that I don't really have a good answer to, the energy consumption calculations. So maybe for future work, that would be a very interesting question to study.
Great. Any other questions? Okay, if not, we're going to take a short 10-minute break, and then at 11:20 we'll reconvene for talks from our postdocs. Thank you. Okay, so our first postdoc talk comes from Chuan-Sun Lee, who is a postdoctoral researcher in Professor Young Chen's group at Purdue. He is an experimental physicist specializing in atomic, molecular, and optical, or AMO physics, and his research interests include quantum simulation, computation, and metrology using ultra-cold atoms and photons. And today he will be talking about atomic quantum simulators in synthetic dimensions. Thank you.
Thanks for the introduction. So today I will be talking about atomic quantum simulators in synthetic dimensions. So first I will give a brief introduction to what that is, and then I will be talking about how we may utilize such a platform to study novel quantum systems, for example, to study novel topological matter. In solid crystals, electrons are moving in a periodic potential made by ions. So to study quantum materials, quantum matter, well, people have developed optical lattice systems where atoms will be in a periodic potential made by optical lattices, which is formed by the interference between laser beams. So this is in the real space, and this has allowed researchers to create and simulate novel quantum matter and materials. And moreover, in this field, people have developed a so-called quantum gas microscope, which will allow down to single site resolution to really study the details of this system, to study, for example, strongly correlated materials. So what are synthetic dimensions? Actually, it can offer another novel way to study quantum matter, quantum materials. So to just give you an example, imagine atoms. There are many internal states in the atoms, and if one can use light to couple these internal states, then atoms can hop between these states. And the coupling between these states is a complex number which has an amplitude and a phase. And the amplitude and phase are determined by the light. And so along the internal state direction, this is kind of like a synthetic dimension. But synthetic dimensions can be very broad. It's not just limited to internal states. It can be any degrees of freedom. For example, people have utilized momentum states of atoms to create momentum space lattice. And I'll be talking about this more later. So keeping this in mind, people have created, for example, a two-dimensional hybrid lattice system where one direction is a real spatial direction, and the other direction is a synthetic dimension. And on top of that, people can even create synthetic magnetic fields for atoms, because to study, for example, topological materials, synthetic magnetic fields will be important to induce topology, novel topology. And these synthetic magnetic fields can be created experimentally by making the round trip phase for atoms to be non-zero. And this is based on the well-known AB effect, where the effect of a magnetic field on charged particles is to create a non-zero round trip phase. So now, experimentally, people have demonstrated this approach to realize, for example, some planar geometries such as a Hall strip. So this allows people to simulate quantum Hall physics, such as to study edge states and localized states. But synthetic dimensions can be very flexible. It may even be utilized to create curved geometry, something like these very complicated geometries. Well, the motivation is that if the underlying geometry of space is non-trivial, well, maybe novel quantum states and phases may emerge. And these novel quantum states may be absent in the planar counterpart. So to give you an example, well, in our lab, we have created Bose-Einstein condensates on a synthetic topological Hall cylinder. So in the Hall strip geometry, we have a real spatial dimension Y and a synthetic dimension S. And experimentally, this synthetic dimension S is composed of internal states of atoms. So now if we couple these internal states by light, by these lasers and radio frequency microwaves, then we can realize this cyclic coupling, you see? And this implements a periodic boundary condition. So effectively, this means that we can connect the two edges of the Hall strip into a Hall cylinder. And interestingly, well, along the real spatial direction, in this case, we actually did not apply any optical lattice. So the density of BEC is actually not modulated along the y direction. However, once we connect the two edges of the Hall strip into a cylinder, the BEC will automatically develop a crystalline structure. I'm going to show you that novel phenomena emerge on Hall cylinder, which is absent in the planar counterpart. So its crystalline structure actually corresponds to a topological band structure shown here. And this topological band structure has these band crossings, which are the nodal points protected by some non-symmorphic symmetry. So if we perform block oscillations, interestingly, you will see that the atoms have to travel twice the period of the band structure to return to the original quantum state. So this is analogous to transport on a momentum space Mobius strip. And since these band crossings are protected by some symmetry, we can even apply some symmetry breaking perturbations to break the symmetry and to induce a topological transition, which will be manifested by the gap opening shown here. And now if we perform block oscillations, you will see that the period of block oscillation becomes the same as the period of the band structure. So in our system, we can image the quantum states as shown here. And we can actually do more. For example, we can control these axial synthetic flux, magnetic flux, to change the band structure such as the band gap, and then to further control the transport. And this is kind of reminiscence of magnetotransport behavior. So I guess the message here is just to show you that with synthetic dimensions, we are able to manipulate the underlying geometry of space and to observe some new phenomena which will be absent in the planar counterpart. So to give you more ideas, well, synthetic dimension can be very broad. It can be in parameter space, for example. So the idea is the following. Consider light-matter interactions. We can couple these internal states by light. Well, the light will induce couplings between internal states, as mentioned before. And this light coupling is a complex number, which includes the amplitude and the phase. So these light field parameters can form a parameter space and can be further utilized to do quantum simulations. So to give you an example, well, experimentally, a synthetic Young monopole has been realized in a 5-dimensional parameter space. So I will not go to details here, but I'm just showing you that some theoretically predicted monopoles, in this case, probably cannot be realized in other platforms, but can be realized in this parameter space, quantum simulators. So the message here is that one may leverage this synthetic space to realize and to study quantum matter and phenomena that could be challenging to study on other platforms. So in our lab, we can actually utilize this parameter space to realize Hamiltonian, which correspond to some 5-dimensional parameter space, and then realize Hamiltonians that can support topological nodal ring and nodal lines in some 3-dimensional subspaces, as shown here. So in this system, well, there are 4 eigenstates, and when the 2 middle states become degenerate, they form the nodal ring and lines in here. So we can realize these nodal ring and lines as shown in this 2D band structure, and we can even further study the evolution of these topological structures. For example, we can continuously change the parameters, and we see that these nodal rings can change the size. But interestingly, you find that these nodal rings can change the size but can never be removed, meaning become gapped. And it turns out that the topology of the nodal ring is actually protected by a second topological invariant, which is beyond the standard term numbers. So there are many interesting topology physics that we can study with this platform. And this has been experimentally confirmed. So moreover, we can also study the evolution of these nodal lines. So by changing parameters continuously, we can see that these topological nodal lines can move, can alter their curvature, can reconnect, etc., but they would never be removed by continuous parameter tuning. Okay. So we're wondering, can we do more with synthetic dimensions? Well, motivated by curved space-time, we were wondering if we can create some synthetic curved space for quantum matter. So for example, a 2-dimensional hyperbolic space. So we wonder, can we assemble and control this synthetic curved space pixel by pixel? Well, then we may look into the mathematical models for such a 2D hyperbolic space. So the models include something like Poincare health plane model or Poincare disk. They are equivalent, but just different models. And let's just focus on Poincare health plane model. And here you can see that there are black lines, which are representing the shortest path between points. So you can see that these lines are curved, not a straight line, indicating that this is really in a curved space. So how we may, well, experimentally realize this curved space? Well, let's think about some square lattices shown here. Well, mathematically, we can make them become equivalent. Turns out if we satisfy these relations. So if we can make, it turns out if we can make an unconventional lattice in the sense that these tunnelings will be non-uniform across the whole system. And also the site energy will also be non-uniform across the system. Then if we can satisfy these relations, we can make these two models equivalent, then we can really realize a synthetic curve space. But this is very, very challenging. You can see that every link will be having different tunnelings, having different side energies. And this can be very difficult to realize in real space. Well, but maybe it may be possible to realize this unconventional lattice in synthetic dimensions. So we were proposing that we can utilize the momentum space lattice I mentioned before. So here, experimentally, we will shine counterpropagating lasers. And each pair of the lasers will uniquely couple a specific pair of the momentum states. So this means that we can really compare each pair independently. And each momentum state will be regarded as some lattice size in a synthetic dimension. And we can generalize this idea to 2 dimensions, as shown here. And interestingly, this kind of system will naturally allow us to have single site resolution. So this seems very promising. So since now when we realize this 2-dimensional momentum state lattice, I emphasize that we have the ability to control every link in this lattice. So with this ability, we can really satisfy the relations I mentioned before for this non-uniform tunneling and non-uniform site energy across the system. So by precisely satisfying these relations, we can make this highly tunable 2-dimensional momentum state lattice become equivalent to the Poincare health plane model, which will describe the 2-dimensional hyperbolic space. So turns out in this setup, it's very possible that the space can even be controlled pixel by pixel and in a time-dependent way. And furthermore, we can even engineer synthetic magnetic fields that will penetrate through this synthetic curve space. So this opens a lot of possibilities to study some phenomena that could be challenging to study in the conventional platform. So for example, maybe we can study quantum dynamics on a hyperbolic surface. So imagine now we can prepare some initial state in the flat space. And then we can suddenly change the curvature of space and to induce a new type of quench dynamics. And it turns out that for any initial state, they will travel toward the funnel mouth, as illustrated in here. And this is due to the quantum funneling effect, where all eigenstates in the Poincare health plane are actually exponentially localized at the funnel mouth due to the curvature of space. So this quantum dynamics is very different from the dynamics in the flat space. And furthermore, we can study something like quantum Hall systems in synthetic curve space rather than in a planar system, which has been intensively studied in condensed matter field. So we can study something like gravitational response of the quantum Hall systems. This is basically the response to geometric deformation. For example, we can study the effects of curvature on transport behavior of atoms. And another example is that we can study the duality of Hermitian systems in curved space and non-Hermitian systems in flat space. This duality is actually highly non-trivial, but has been recently established theoretically. So experimentally, we can verify if this duality is true. If so, we can actually create curved space to explore novel non-Hermitian topological physics, which are not able to study in the usual Hermitian quantum systems. And we can study exceptional points which could be important for quantum sensing, for example, from the curved space perspective, without really engineering the dissipation. So rather, in a system without dissipation, by creating curved space, we can study this non-Hermitian physics. Okay, so finally, I would like to thank our lab members and the collaborating series. Thank you very much.
Do we have any questions? Okay, great. If not, we'll move on to our next talk. Our next talk is from Dr. Vahagan Makitarian, who is a senior research scientist at Purdue University. He earned both his bachelor's degree in electrical engineering in 2010 and his master's degree in plasmonics and photonics in 2012 from Yerevan State University in Armenia. In 2013, he began his doctoral studies at ICFO, the Institute of Photonic Sciences in Barcelona, Spain, and received his PhD from UPC in 2018. His current research interests include using machine learning assisted photonic inverse design to enhance light-matter interactions, light-induced physics and control of quantum states of matter, spectroscopy of topological quantum materials, and investigating quantum many-body physics through Rydberg atom array-based quantum simulators. Thank you.
Yep, can you hear me? Yep, good. So thank you everyone for being here at this late time in a summer school and willing to listen to the talk. So I'll be talking about our collaborative effort on trying to study a many-body interacting spin systems on Rydberg atom array quantum simulator. As you can see, it's a pretty large collaboration at this point. This is a work initiated under the umbrella of the Quantum Science Center, where Purdue is part of it. Actually, almost all the members except Amazon is part of that, part of the Quantum Science Center. But the initial collaboration was established between Purdue and Quera, and we use the Quera's quantum simulators, neutral atom-based quantum simulators to study this many-body system. So I want to specifically emphasize that there was an immense amount of work done by our Quera collaborators, particularly Milan and Fangli were very active at the initial stage of the collaboration for the theory development, etc. So the model that we are trying, study, it doesn't display on these slides, unfortunately, but it's an Ising type of Hamiltonian of interacting spins. I don't know why that Hamiltonian doesn't show here, but the spins are located on the lattice that you're seeing on the left. And the good thing about this model is that it's exactly solvable, meaning that you can find the ground state spin textures of the system, spin states of the system. And for us, it would have been an easy way of benchmarking the Quera's machine's capability, because the collaboration started like 2 years ago, and it was just the beginning of the Quera also when it came online. But the second motivation behind this project was that actually these spin systems can be realized in real materials, and some of these rare earth tetraborates actually follow the Shasti-Sunderland model. By studying them, we could kind of prove the concept that you can use this kind of neutral atom-based quantum simulators to study real materials and try to find the magnetic states of these real materials. And finally, our collaborators from Oak Ridge and Purdue also studied the system previously using D-Wave machine, and they found some of the classically known phases, like fractional magnetization phases in the system. So this knowledge would have been helpful. But we are working with Quera's machines. Professor Michel Lukin yesterday gave a good introduction, so I might maybe skip this part, how they do the state preparation. But we were working with the Quera's Aquila machine, which was available to us through Amazon bracket service. So everyone who is interested in doing any experiments with neutral atom arrays, you can actually go to the bracket service and get access to the machine, queue your time, and then do experiments, paying a certain amount of money for that. For those who were not in Misha's talk, maybe I will briefly also introduce the system. The Rydberg states are these highly excited orbitals of neutral atoms, and I apologize. A lot of things do not show on this slide, I think, because maybe we should download it from the Google Drive. Yeah, sorry about that. Give me a sec. Can we download it? Sorry about that. Yeah. Let's try. Oh, yeah. Sorry about that. Hopefully this will be better. There we go. Yeah. So for just to quickly also flash the Hamiltonian itself, it's basically Ising type of interacting spins where the spins are located on that lattice and the interactions are this nearest neighbor interactions between the spins. Will not be very useful. But Rydberg atoms are these neutral atoms states that are highly excited, that have large principal quantum number. So it's a highly excited Rydberg atom state. Why they are useful is that the excited state lifetime can be very large because it scales as a cube of the principal quantum number. The second thing is that the radius of the excited state scales quadratically with the principal quantum number. That means the orbital, the radius of the electron orbital is very, very large. And normally it's in order of the microns. And if you look at the ground state orbital, the ground state is very tiny. So the radius is very small because in this particular case, they're using the 5s1/2 as a ground state. That means the coupling, because of this less overlap between the orbitals, the coupling between ground state and excited state will be small. That's good because then if you excite the system, then it will not couple to the ground state. It will not easily decay. So you can have the coherence, larger coherence. But it's also hard to couple from ground state to excited state. So they use this very complicated two-photon photoexcitation scheme with intermediate state. Okay. Because of this large radius, then the interactions between the excited states is being large, which I'll comment in a second. But there's also a drawback for this large principal quantum number. If you take two excited Rydberg states, then the transition between them scales as quadratically with the transition dipole moment scales quadratically with the principal quantum number. That means you can easily go from Rydberg state n to Rydberg state n-1 by just through this large dipole transition. But a good thing is that these transitions are happening at very low frequencies. And at low frequencies, there are no available density of states for these transitions to happen, for the vacuum photons to trigger the spontaneous decay of the system. Because from the Fermi golden rule, you know that the probability of this transition is proportional to the local density of states, and local density of states scales quadratically with the frequency. Okay? But if you forget about this complicated structure of the atom and real experiments, you can think of it as a two-level system that's excited resonantly with some detuning from the resonant state. And if you look at the dynamics of the system of a single atom in this excited single atom, then it will just go do the Rabi oscillations, coherent Rabi oscillations between excited and ground state. Nothing too much interesting. But if you bring the second atom to the neighborhood of the first atom, they're identical, they will start interacting. Once both of them are excited, they will start interacting. Because the interaction happens only when both of them are excited. And the scale of this interaction is very, very strong. It actually scales 11 degree of the principal quantum number. And you remember we were going to very large principal quantum numbers. That means the interactions can be scaled orders of magnitude. And that's one of the key mechanisms that allows us to do this simulation. So if you look at the possible eigenstates between the two atoms, you will have both atoms in a ground state, both in one of them being excited, the other one in ground state, but they're identical, so you should take the superposition of those. And when both atoms are excited. But when both atoms are excited, they interact, and that interaction energy shifts the energy of that double excited state. Which means at some point, if you keep your excitation resonant and you bring them together, at some point this interaction will not allow you to excite this double excited state, so you will only be left with the possibility of being both atoms in a ground state and one of them being excited. And that doesn't happen only with two atoms, it happens in arbitrary configuration, so you can have n atoms within that certain radius, which is called Rydberg blockade radius, and only one of the atoms will be excited in that configuration. This mechanism is called Rydberg blockade, basically. So it doesn't allow to have more than one atom excited in the system. And if you arrange your atoms now in the lattice structure, then you can think of it creating the spin textures. For example, in this case, if you have a square lattice with a nearest neighbor distance such that atoms' neighbors are within the blockade radius, then you will only have one atom excited, another one de-excited, so you can think of it as a spin-up, spin-down configuration for these atoms. Okay? So if we realize this Shaste-Sunderland lattice, so that we place the atoms in that system, the Hamiltonian will look like this one. So you will have this van der Waals interaction term, and you will have a pump term. And if you look at the van der Waals interaction part, that's basically the same Shasty-Sunderland model I introduced for the spin earlier. If you remember that the population number is proportional to the sigma z operator. And, but on top of that, we also have this drive term, which introduces fluctuations in the system. This drive term is trying to flip the spin at each atom. And that will introduce many body fluctuations in your system. If you look at the classical phase diagram of the system, so when you don't look at the Rabi term, then you would recover what's known already classically. But it turns out that this drive in a system, so, and what's known is that you are actually expecting to see this fractional magnetization state, which means the spin magnetization of that particular interaction parameters, for example, V2 over V1 ratio and delta over V1 ratio, you should expect the ratio of the magnetization to the saturation magnetization to be 1/3. It's fractional. And there are many of these kind of fractional states in the system, and most of them are known to be living at the boundary between this classically known 1/3 phase and the nil phase. So at this boundary, you have infinite many degenerate states that live, but they don't occupy finite phase space. Okay? It turns out that the presence of this Rabi term actually that was one of the first surprises to us when we did the DMRG studies of the system, that this fluctuation stabilized these known classical phases, the degenerate phases, into much larger phase volume. Okay? Well, the second surprise was that this classically known quantum dimer phase, which is essentially some ordered state of dimers living on that short bond of the lattice, acquires some quantumness. So those were two main predictions that came from the theory. And we did some analysis of these states. For example, for the quantum dimer phase, why we thought, we suspected that there will be quantumness fluctuations is that if you would look at the classical dimer phase in the classical model, then you would expect that to, if you look at the correlation, Fourier transform of the spin-spin correlator, which in this case is a number correlated between the atoms, you would expect a well-defined peak at pi 0 position in the momentum space. But what we see is blurred distribution for the momentum space. That means basically your spins are not well ordered, but they are fluctuating. So it's random, classically random, but quantum mechanically they are just superposition state. So we defined some operators that would check this quantumness. We checked the dimer occupancy. We would check whether on that short bonds we have dimers occupied. And if you would have classical dimers that would have only up and down or vice versa, you would expect the expectation value to be plus minus 1. But what we see in experiments, if it's fluctuating, you would expect that the expectation value to be 0. And from the simulations, we actually see that the expectation values are 0. That means our dimers are fluctuating. They are not ordered dimer states. And if you check the square of that operator, you would expect it to be close to 1. And the dimers are spatially also, the correlations are exponentially decaying in space. So if you take the dimer and look at the flip here of that dimer compared to well, in this case, occupancies. But if you look at the correlation of that D operator in distance, you will see that these correlations decay exponentially, which also tells you that the system is classically random. But it's not random, it's basically quantum superposition state. And if you check also the correlation of the dimer flip, so if you apply an operator that would flip this dimer to its opposite, then if you are expecting any correlations, then you should expect non-diagonal elements between this dimer correlator. And it turns out to be there. So these dimers are highly correlated in our system. Okay, but in order to address the role of these quantum fluctuations and the stabilizing these phases, you can actually reverse the system. You can go back from this quantum system to the classical regime by just reducing the Rabi term compared to the van der Waals interaction. And if you do that, then you will see that actually that reduction of the quantum fluctuation term is shrinking this phase volume of that new phases to a much smaller domain. Okay. Now, after doing all this analysis from the DMRG, we needed to do experiments. So experimentally, you only have access to the population numbers of these Rydberg states. When you quench, you look at which atoms were excited. in order to to differentiate different phases experimentally, you need to have some order parameter. An order parameter for us was the structure factor, amplitude of the structure factor, which is nothing more but this Fourier transform I mentioned earlier of the number correlated on the lattice. And if you look at the phase diagram, specific points, you will see that those specific points correspond to specific ordering of the excited, de-excited atoms, so it's corresponding to specific spin texture. If you do Fourier transform, you will get the peaks at specific k point values. And you can take those amplitudes of that k points to be your order parameter. When you're sweeping the interaction, you can look how this order parameter is changing from region to region. We also needed to deal with, because we are always dealing with the finite size systems, you need to take care of the boundary conditions in order to mimic this thermodynamic limit, where you have infinite lattice. And the physics we normally discuss, this exact solvable model, it's in the thermodynamic model. And to do that, we use some extra atoms at the boundary to basically passivate some effects that come from the boundary, finite size effects. Then we did first experiments for the fixed parameters. On the left, you see in each panel, you see for say 1/3 phase, the calculation, the MRG result. On the right is the experimental realization of the same interaction parameters. And you can see that the peaks of the correlator or corresponding structure factor are recovering the expectation from the theory. And this was the first time experimentally we've seen that this 2/5 phase actually exists in our system. And that's, as I explained, because of these fluctuations we have on top of the classical model. We also checked the quantum dimer phase, and we checked the dimer occupancy. And as predicted from the theory, we also see the expectation value of this dimer occupancy to be 0, which also confirms that we have this fluctuating phase. After that, we did a more extensive study. We did the phase diagram mapping, so you change the interaction parameters, and then look how specific phases are occupying by choosing this order parameter as your differentiation method for your phases. And for different boundary pinning strategies, we could recover. So if you look at the 1/3 phase, 2/5 phase, nil phase, you can see that they occupy wherever you were expecting the interactions, where the phases to be. But also the strategy of the boundary pinning is also affecting how well you can recover the phases. So when you do experiments, you need to be careful with this effect. And also the dimer correlations were in the region where we were expecting the dimer phase to be. So experimentally, essentially, we confirmed all the predictions from the theory, which was the appearance of the 2/5 phase, these new phases, and also that the dimers become correlated, so we can become quantum dimer phase. And that's it. With that, I'd like to also mention that a big part of the experimental work was funded by Amazon Bracket team, and some other part was covered by the Quantum Science Center. So I would like to thank them for the support. Thanks.
Great. Are there any questions from the audience? Great. If not, thank you, Hagen. We'll move on to our next talk, which is from Ryan Linehan. He is a postdoctoral researcher at Fermilab, and he spent his PhD at SLAC and Stanford building the xenon-based dark matter detector LZ, and published the world's most sensitive WIMP dark matter search to date, and then pivoted to focus on quantum sensors for light dark matter detection. His current interests include understanding and modeling TLS and quasi-particle dynamics in superconducting qubits, and developing quantum acoustic devices for low-threshold dark matter detection. Thanks.
Thank you. All right. Hi, everyone. My name is Ryan Linehan. I'm a postdoc working at Fermilab with the QSC. I'm here to kind of round out the science talks with we're going to pivot back to quantum sensing and how we use some of our quantum technology for basic science. And so more specifically, we'll talk a little bit about listening for dark matter with quantum acoustics. I'll try to go reasonably quickly, but it's useful to provide one slide of context. For those who were here yesterday who saw Tally's talk, this is just a quick reminder that when you're searching for dark matter, which we haven't seen actually interact with a terrestrial detector yet, one of the important things to recognize is that to look for lower mass dark matter, you need phonon sensing. And so what that typically involves is building a dilution fridge, having a cryogenic substrate with something like a superconductor present, and looking for scatters of dark matter on your substrate that produce phonons. And in general, the paradigm so far has been to build a detector that is made of a superconducting film with some kind of sensor on it, like a transition edge sensor or an MKID. And those phonons will go and break Cooper pairs in that sensor into quasi-particles, which can then be sensed. Okay, so as I said, mostly for the last 30 or so years, we've been searching using these other, these TES technologies. Haven't found anything yet. But the interesting thing is that in the last few years, the dark matter community has actually found some inspiration in quantum devices, right? So in particular, superconducting qubits have been a very appealing choice of detector type for looking for dark matter scatters on these substrates. So I want to sort of give a brief intro and some context to what these are for those who are maybe not used to looking at these. Superconducting qubits are basically a film that is patterned with a superconducting circuit, some coplanar waveguides and some capacitors and inductors in that film, lying on top of a thicker substrate, silicon, germanium, what have you. And from the top, it looks like this. The qubit itself is this little cross that forms a capacitor to a ground plane. There's a Josephson junction or a squid right here, which you can't see because it's too small. And what it does is form an anharmonic LC oscillator. So you get a ground state and an excited state. You use those as your qubits, and you don't worry about exciting to the next state. They're typically coupled to these kind of readout resonators and read out with microwave/RF control. So that's that's pretty simple. You have a feed line that is on your chip. You send a signal down your chip. It hits your feed line. It goes down your feed line. It interacts with your resonators. That talks to your qubit. Okay, great. Now these things have inspired certain devices in the particle physics community that are looking for very, very sensitive, very, very small energy depositions. One example being this squat technology that's came out of SLAC. And what I want to do is actually talk about a slightly different way to use these superconducting qubits than the standard way where you just have phonons that break Cooper pairs into quasi-particles and you sense those. And this is actually much more quantum and is something that maybe people here are more familiar with. This slide deck is usually meant for particle physics folks, so I'm sort of retooling it for people who know more about all of this than all of that. But in principle here, what I want to talk about is resonant energy exchange, which is basically what happens when you have two quantum systems, say a qubit and an electromagnetic resonator, both of them are either an anharmonic or a harmonic oscillator, and you bring them on resonance, right? So you can write down a Hamiltonian, relatively simple Hamiltonian. There's an energy of one oscillator, there's an energy of another oscillator, and then most importantly, there's this coupling term. And what happens when you bring them on resonance and make the frequencies roughly the same is that the total system evolves by swapping a quantum from, or an excitation from one system to another, right? So this is a Q-tip simulation of exactly the system. On the x-axis is the oscillator detuning, so basically how close your qubit frequency is to your resonator frequency. And on the y-axis is time, and on the z-axis is effectively a metric for how occupied the qubit is. So if you start with the qubit in the excited state down here at the bottom and let the system evolve, you get these nice Rabi oscillations if you're pretty close to on resonance. And if you're off resonance, you don't really get those Rabi oscillations much. So we want to actually take advantage of this because this is nice and shows that you can actually transfer information that is at the kind of 10 micro EV scale, whatever the splitting between your ground and excited state is. And that's advantageous for, in comparison to some of the other techniques. Yes, was that a hand? Aha, yes. So that is because I've included dissipation in this as well. So there's a T1 loss as well that you get just because there's an environment simulated. Yeah. Parameterized in this, but yeah. So you'll always have that. Okay, so also please throw out questions if you have them. Okay, so now the interesting thing here is that as long as, if you look at this Hamiltonian, as long as you can achieve G, that coupling between your two systems, they don't need to be electromagnetic only, right? We were talking about a qubit and an electromagnetic resonator. Here, we can actually talk about a qubit and a phononic resonator. So like kind of a high overtone bulk acoustic resonator, which is basically a standing mode between the top and bottom of faces of a chip. And so this is where we kind of enter this world of quantum acoustics. We want to be able to swap phononic quanta, so phonons, single phonons at the 10 micro EV level, into an electromagnetic cavity. Here, this is a 3D transponder. It looks a little different from on the previous slide, but into a qubit, and then read that excitation out using our readout resonators. And this has actually been done. People have injected phonons using the same technique operated backwards in the literature. This is a paper from 2018 showing basically the same thing I showed on the last slide, except that was simulation and this is data. And notably, if we can inject, we can detect, right? We can run the system the other way. So that's exciting. If we can detect, we can count, right? So we can basically say, in one little iteration of the cycle, we tell the qubit to wait on resonance, try to see if there's a phonon present in your phononic resonator, move off resonance, determine whether the qubit is in the ground or excited state. If it's in the ground state, maybe we didn't see a phonon. If it's in the excited state, maybe we did see a phonon. And that way you kind of get this bit stream of like information about whether or not there's a phonon in your cavity. Okay. So just to transition a little bit into some of the other diagrams that I'll have, you can actually do this with the flip chip quantum acoustic device. So it looks a little different than on the last slide. Here you can make two chips, one with the H-bar, the phonon mode, and one with the qubits that are actually reading that out. And the way that this works is you basically have a phonon mode here with lots of nodes and antinodes between the top and bottom of the chip. There's a piezoelectric here, and that couples to your electromagnetic fields that are kind of related to your qubit operation there. This is potentially advantageous because for a number of reasons. One is that you can separate the development of your H-bar chip from the development of your qubit chip and kind of parallelize those, which is nice. You can also use it as a veto or even a trigger for looking at radiation crossing through both chips, right? If you have a cosmic ray that passes through both, you'll see phonons in the top chip, but you'll also see phonons in the bottom chip, and those can destroy your coherence in these qubits here. If you have some extra qubits that are kind of monitoring for that, then you know that wasn't dark matter that hit this chip or something like that. Or you know to exclude that period of data taking. And then lastly, scattering in the H-bar chip doesn't actually negatively impact qubit performance, which is nice, but that doesn't happen if you only have a single chip. So these are just some things to introduce what this flip chip architecture looks like and motivate it a little bit as a detector. So then the real question is, this is all good and well, but we really should try to assess how sensitive this might be to new physics. And so this is where I'm going to introduce kind of a recent paper that we put out in November, considering some of these things and trying to understand how well matched this is to some of the tasks for searching for new physics beyond the standard model. So one, you need to know the sensitivity. You need to know the swap efficiency. Basically, how efficiently, if I have a phonon in that mode, can I swap it out into a qubit for readout? And that really depends on how well spatially matched your electric fields are in your qubit to your piezoelectric transducer. If you are completely offset and your transducer is way over here for some reason, and your electric fields are oscillating here in your qubit, you're not going to do anything. You're not going to be able to couple that mode to that qubit at all. But if they're nicely matched and the mode structure looks nice, roughly the same size, then you get a reasonably high coupling G. The next thing you need to know is that there's lots of very interesting mode structure present, right? So I've sort of shown this phonon mode that has a lot of nodes and antinodes in Z here. But if you actually go into the details, there's lots of different modes in R as well. So this is kind of a plot of some of these modes and what they look like. So you get this rich structure of the modes, the radial structure of these modes, and all of those sort of evolve at the same time together as part of the system. And that dictates how efficient your transfers can be back and forth. And lastly, and that sort of alludes to this last picture here, which is a more refined version of the Rabi oscillations that we were showing earlier, where if you start off in a single phonon mode, here being yellow, you can see that excitation slosh into your qubit, which is in black here over time. But it also sloshes into the other phonon modes because the qubit allows that excitation to slosh back. So you get efficiencies something on the order of 70% per our prediction. So the other thing you need to know to understand how good of a detector this can be is sensitivity. So how often do you get 1 when you're not supposed to get 1? Basically, how much noise do you have? And here, the basic picture is that we expect a noise at the kind of percent level or so for kind of current systems. And those are driven by spurious qubit excitation and readout fidelity. So if you have hot quasi-particles or TLSs exciting your qubit, then those can cause false alarms or mimic fake dark matter signals. And if you have readout fidelity that's not like immaculately great, then you also will run into problems there. So this is particularly bad as you go down in frequency, because as you go down in qubit frequency, in phonon frequency, you start to near that thermal floor, which is not, you start to get to the point where you're nearing the creation, you start to really enhance the rate of phonons created just because a dilution fridge can't go infinitely cold. And then lastly, okay, now that we've talked about a little bit of the efficiency for swap and of the dark count backgrounds, one of the questions is actually what kind of signals can we measure? And we can actually write down some sensitivity to wave-like dark matter, which I'm actually not going to show here because I talked about scatters initially. But one of the interesting things is that for detecting scatters with this, there's an actually very interesting engineering challenge where the phonons produced in a scatter, there's going to be lots of phonons, right? At the milli-eV scale or 100 milli-eV scale, there's a good amount of energy relative to the 10 micro-eV that's present in this H-bar. The problem is that those phonons often have too much energy, right? So how do you get a milli-eV scale phonon down to 10 micro-eV? And that question is not, the answer to that's not trivial. We have some ways that we think we can downconvert phonons based on literature in the quantum computing superconducting qubits community and based on literature from the dark matter community. So we're really marrying these two communities and trying to find ways that maybe you can send a phonon into a superconductor that has a low gap and have that launch into a phonon mode at a particular energy. But that all being said, we have some experimental campaigns to explore this going forward. And those will happen at Fermilab. I'm not going to talk a whole lot about this, but basically we have 2 facilities, one underground in the Minos Hall for testing low background environments, and one on the surface for high throughput. So there's lots of interesting things that we're going to be doing at Fermilab to test these and to explore the potential of these as sensors going forward. But all that said, we have a particular goal in mind for a kind of detector that we want these to try to be, and we're exploring that in the near future. So overall, we found that the qubit-coupled H-bar is a promising technology that we really are interested in trying to see how well it works in our field for particle detection. And it uses fundamentally 10 micro-eV acoustic phonons, which is kind of 2 orders of magnitude better than the energies, or smaller than the energies that we can sense with other kind of leading technologies in the particle physics and dark matter fields. We did a bit of a sensitivity study, so that there's a lot of details in there. But overall, over the next year or so, we'll be doing some more experimental probes of this as a promising way to potentially detect dark matter. So this is our team. We have folks from UChicago, UCSD, Northwestern, Fermilab, and IIT, and happy to take questions.
Great. Any questions?
Now or later. So we can keep going, I think.
Sure. Great. So that wraps up the postdoc talks that we had today. And now we're going to move into the last talk of the summer school, which is going to be by Sebastian Morguitio Ramirez, who is a assistant professor of philosophy at Purdue. And from 2021 to 22, he was a postdoctoral fellow at the University of Oxford. He earned his PhD in the History and Philosophy of Science program at the University of Notre Dame, where he also completed a master's degree in physics. His research focuses primarily on the history and philosophy of physics, and he has published over a dozen articles in peer-reviewed journals across philosophy, history, and physics. And soon, in this summer, he will be joining Princeton University. Thanks.
Okay. Okay, well, thanks for the invitation. I'm very happy to be presenting this talk, especially on the occasion of the 100-year anniversary of modern quantum mechanics. We are going to talk about what exactly that means. This is going to be very different from the other talks, but I hope you see that there are more connections than what you might expect between the more philosophical foundational questions going back in the 20s and 30s and some of the applications of quantum mechanics, especially after the 1960s and 70s. So this is a caricature of the history of quantum mechanics narrated from the perspective of Einstein, right? So let me just read this. Einstein, oh sure, brilliant guy, relativity, gravity, the photoelectric effect, but when it came to quantum mechanics, the poor man just couldn't handle it. He wanted the universe to be neat and tidy, like a Swiss watch. He couldn't stomach the idea that nature is fundamentally random, that particles don't have definite positions until you measure them. God does not play dice, he said, adorable, right? Now, this is ChatGPT, but it's actually a very common kind of stereotype of the classic story of the quantum mechanics in the 20s, 30s, and 40s, especially and a bit more seriously. People say, look, Einstein was too fixated on trying to recover determinism. He was too worried about locality, and he just never kind of gave up the classical worldview in some sense. And then he was fighting and debating with these other physicists like Bohr, Heisenberg, Pauli, Dirac, Jordan, von Neumann. And in those debates, with a lot of thought experiments, it became clear eventually that people just said, look, Einstein, well, it might be weird in some ways, but this is what it is, and this is how quantum mechanics works, and you have to get used to it. And then the story goes like decades pass, and eventually we show that, or I mean, experimentalists show that the kind of view about the world that Einstein wanted to preserve, you couldn't do it. And Einstein lost that kind of battle, so to speak. That story is wrong in many ways, and I hope during this talk to at least show you some ways in which it is wrong. So my main goal is to show ways in which the standard story is wrong, and also show ways in which Einstein's own philosophical insights and more interpretational and foundational worries about quantum mechanics was actually crucial to the development of the theory as we know it today, and to many applications that came to emerge in the 60s and after that. Okay, so this is 100 years, so what was happening 100 years ago exactly? This is the celebration of what exactly? Well, it's controversial, right? I mean, quantum mechanics, there was an old quantum theory, right, by Bohr, and then Bohr and Sommerfeld, and it worked to a certain degree. It was very successful for the hydrogen atom, but then when they were trying to add more electrons or trying to figure out how to get the spectral lines for molecules, things were falling apart. Here is Heisenberg on April 1925. So 100 years ago, kind of exactly. The present state of quantum theory, one must rely on symbolic model-like pictures that are more or less built on the mechanical behavior of electrons in classical theory. Heisenberg was the assistant of Born, who 2 years before that said, it becomes increasingly probable that not only new assumptions will be needed in the sense of physical hypotheses, but that the entire system of concepts in physics will have to be rebuilt from the ground up. They were trying to come up with selection rules for more complicated systems, and they were failing, and they were frustrated. This is April 1925. Then the story is that Heisenberg got a high fever, and he went to recover in the island of Helgoland in Germany. And during that time, while recovering from high fever, he just had this kind of way of thinking about things very differently from what he was trying before. He said to Pauli, July 1925, all my wretched efforts are now devoted to killing the concept of orbits, which cannot be observed in any way. So again, they were trying to work with this kind of planetary system of the atom, and they were trying to use orbits and figure out how to do that. And Heisenberg kind of gave up in this island and said, no more, it's not working. And then he published his famous paper, the first paper in which we eventually will call matrix mechanics, but he didn't have matrices yet. In that paper, he says that his goal is to establish a basis of theoretical quantum mechanics founded exclusively on relationships between quantities that are observable. And he very explicitly says he's not going to try to do this through the trajectories of spatiotemporal trajectories of electrons or orbits. You cannot do that. So let's focus on transition, amplitudes, and energies, and that kind of stuff. That's what the new program by Heisenberg that was proposed there. Then from this moment, July 1925 to more or less the fall of 1927, it was a crazy year for quantum mechanics. More than 200 papers were published in that time, all or many of them very important. So just to give you a sense, Jordan and Born showed that you can use matrices, which were very weird to the physicists at the time. You could use matrices to kind of capture some of the quantities that Heisenberg was calculating in that paper. Then there is a famous paper by Born, Jordan, and Heisenberg, November 1925, in which that's what we will call now kind of the standard matrix mechanics, like where eigenvalues, eigenvectors, observables, that kind of thing comes in that paper, that kind of formalism. But they're very explicit that they're not trying to model the electron as an object that has a spatiotemporal trajectory. Then, in 1926, Schrödinger publishes a series of papers introducing what we now call, or it's sometimes called wave mechanics, the Schrödinger equation, trying to do things with his equation and showing like how the wave function can be used to calculate many things that Heisenberg was doing in a very different way. Schrödinger didn't like what Heisenberg and Jordan were doing because he thought they were kind of giving up. They're like, okay, you can find these nice rules, but what exactly do they represent? And Schrödinger was not happy about that, so he thought of trying to come up with a more intuitive approach in which quantum stuff are understood as waves in some sense. But Heisenberg didn't like that, and then he said, even if a consistent wave theory of matter in the usual three-dimensional space could be developed, it would hardly yield an exhaustive description of atomic processes in terms of our familiar space-time concepts. Okay, finally, well, I mean, there are a lot of things to say, but this is a very quick review of those 2 years. Then in the spring of 1926, it was proven that matrix mechanics and wave mechanics were equivalent, and that kind of was good and bad. Was good because these programs kind of realized that they are kind of doing the same thing and they can do it either way, whichever way is more efficient or easier. It was bad because it was confusing what exactly these things tells you about the world, and they were still trying to understand what exactly atoms are, what exactly electrons are, and it just was very confusing. As I said, more than 200 papers were published in that time. Then you have the paper by Born, 1926, where he's doing Born scattering, and he shows that probability, I mean, he gives the Born rule, basically, right? So you take the square amplitude, and then you calculate the probability of getting the particle in a certain, you interpret that as a probability of getting the particle in a certain position, or whatever the property is. Then the Solvay conference, in 1927, at that point it was like physicists, especially Heisenberg and Jordan and others, said, we are done, we did it. We came out with foundations for quantum mechanics, and they work, and we are solving a lot of problems that you were not able to solve with the Bohr model of before, and there was like a sense of enthusiasm and victory, I guess. And then Einstein was not happy, and then Einstein said, your theory might be a correct theory of statistical laws, but it is an insufficient conception of the individual elementary process. So this is going to be important throughout the whole talk that I'm giving, like Einstein always kind of being cautious and trying to figure out what exactly means what you are doing with this probability stuff. Okay, so that was all 2 years. This is a short talk, so I cannot do this for every 2 years in the history of quantum mechanics, but I'm going to give you some highlights. So here are 2 phrases that you hear all the time in science talks, even in the media, in popular talks and things like that. God does not play dice, there is spooky action at a distance. These things have been taken out of context, and people repeat them all the time without like really understanding what exactly Einstein was trying to say with them. So my goal is to give you a bit of more subtle, nuanced picture of Einstein's actual criticism of quantum mechanics. At the end of the day, the main problem can be summarized like this. Schrödinger introduced this thing, the wave function. Okay, what is that? I mean, mathematically, we know what it is, like a ray in Hilbert space, sure. I mean, you can give me all the mathematical properties. But that's not the question. The question is how that connects to the real world. You have the real world there. You have electrons and atoms doing stuff. You have the formalism. And the formalism works. But saying that something works is not enough. You want to understand what's actually going on. And so a lot of these debates, at the end of the day, can be boiled down to what or how exactly does the wave function represent physical properties, the actual external world. That can be summarized as the main question driving some of these debates. So already in 1927, Einstein came out with a thought experiment motivating that, or trying to suggest that there is something very strange with this probability interpretation of the wave function and Born's rule. Very briefly, he said, what if you have like a small hole and you throw one system, one electron if you want. And you know it can be detected, say, in A or B. But if it is just a probability, and it's like a wave, because Schrödinger insisted this is like a wave in 3-dimensional space, at least at first. The problem is that if you have 2 particles, that is more than 3-dimensional now. It lives in configuration space, and it doesn't work like a wave, like a water wave, which is in 3-dimensional space. So that already showed that if you add more than 1 particle, the picture that Schrödinger wanted kind of breaks down. But this is just 1 particle. So in theory, you can imagine the wave function as a wave in 3-dimensional space. And Einstein asked, why couldn't you detect the particle in both A and B? If it's a wave, it passes, and it presumably touches all this surface of this detector there. Why couldn't be detected in both places? It cannot be if it's just 1 particle. If it's detected in B, it's not going to be detected in A, but this is kind of an instantaneous thing. So he was kind of, at the end of the day, asking, how does the reduction of the wave package works? Like, you keep throwing this wave, but how exactly that works? What's going on? Now, this is the most cited paper, at least in the Foundations of Quantum Mechanics, by Einstein, the EPR paper, 1935, with Podolsky and Rosen. This is supposed to show a more clear way, or it's supposed to be Einstein's main criticism of quantum mechanics, his famous incompleteness argument. It turns out Einstein didn't like that paper, and people shouldn't cite it that much. He was actually upset with the paper. It was written by Podolsky, and it seems Einstein didn't even have time to check it before it was submitted. Einstein said in a letter to Schrödinger, for reasons of language, this paper was written by Podolsky after many discussions, but still it has not come out as well as I really wanted. On the contrary, the main point was, so to speak, buried by erudition. It turns out that if you want to understand what Einstein's criticism of quantum mechanics really is, especially the incompleteness argument, don't look at this paper. Look at his correspondence with Schrödinger and look at a later paper in 1948 called Quantum Mechanics and Reality. That's the clearest exposition of Einstein's own dissatisfaction with the theory. I'm going to give you a taste of how it works in a moment. Okay, so notice in the 2 years that I mentioned, 1925 to 1927, there was no discussion of entanglement. People were not discussing entanglement yet. It was kind of there implicitly. Schrödinger has some notes where he realized there is something weird going on, but he didn't publish them. Heisenberg-Jordan didn't notice this. It was Einstein in his correspondence with Schrödinger in the 30s who kind of highlighted the importance of paying attention to entanglement and saying, you know, at the end of the day, what's weird about quantum mechanics is entanglement. And that only came out in his discussions with Schrödinger. And now we all talk about entanglement, but it was not really at the forefront of the discussions in the original kind of formulation of quantum mechanics. And you may be thinking, okay, that's why Schrödinger's cat is important. No, Schrödinger's cat is really a copy of Einstein's own thought experiment, the gunpowder experiment. Here is Einstein. The system, imagine a system is a substance in chemically unstable equilibrium, perhaps a charge of gunpowder that by means of intrinsic forces can spontaneously combust, and where the average lifespan of the whole setup is a year. In principle, this can be quite easily be represented quantum mechanically. In the beginning, the psi function characterizes a reasonable, well-defined macroscopic state, the gunpowder there, whatever it is doing. But according to your equation, the Schrödinger equation, after a year, this is no longer the case, right? Because it has a probability of decaying, and you might have a superposition. So he says, the psi function then describes a source of blend of not yet and already exploded systems. This is Schrödinger's cat, dead and alive, a month before Schrödinger's cat. Actually, Schrödinger recognizes this and says, I created an example very similar to your exploding powder keg. And then he goes on to talk about Schrödinger's cat. The point here is Einstein already had realized that one of, I guess, the maybe weirdest thing about quantum mechanics is, well, first, entanglement, and second, how to deal with microscopic systems. When does the wave function collapses and why? There is no mechanism. It's a rule. Collapse postulate. Sure, but like when am I allowed to use the collapse postulate? When you do a measurement. What's a measurement? Is it a physical interaction? Why don't you get a superposition of the device and the system? Nobody was answering this. It was put by hand, right? So the Schrödinger's cat comes out in this discussion from Einstein, but Einstein was first. That's my point here. And then Einstein uses entanglement to come out with his more forceful criticism of quantum mechanics. It's not indeterminism. It's not the dice thing. None of that. It's a deeper problem. Here is the problem. So I'm going to go quickly, but here are 3 assumptions that you need to understand in the incompleteness argument. First, locality. A and B can only affect, so imagine A is like unobservable or something happen like the particle in this arm, and B, the particle in this arm, like in a entangled kind of setup. A and B can only affect each other by means of physical processes restricted by the speed of light. Why? Well, special relativity. Einstein wants his special relativity to be still true. There is a second assumption that people skip all the time, and actually for 60 years or so, it was ignored. But it's very important, otherwise you don't get the predictions, and actually if you don't have this assumption, the Bell inequalities don't make any sense either. So here is the assumption, separability. If A and B are spatially separated systems, then A has a physical state and B has a physical state. So you have, say, 2 electrons that interacted, or 2 photons, whatever. 1 electron is here, 1 electron is here. You're about to measure this one. Einstein is saying, look, if you really have an object here and an object there, then there has to be a state for the object here and a state for the object there. What state? I don't know, but objects are physical things, and physical things have states. So if you're telling me that really there is something here that you're going to measure, and here other thing that you're going to measure, you better think they have states, according to Einstein. And then you have this definition of incompleteness. He's trying to show that there is more than two wave functions that you can assign to the same physical state. And not, I mean, two different wave functions, incompatible wave functions that you can assign to the same physical state. If you show that, according to Einstein, you show quantum mechanics is incomplete. So here you have the two particles. This one goes there, the other one goes there. If you have separability, it follows that A has a state and B has a state. Why? It's two different objects separated in space. So they have to have states according to separability. Now, you're going to make a measurement here, and you do it, and you get yellow. Once you know you get yellow, because these are entangled, you can say the other one is blue, say. Blue there. So yellow, blue. OK. But here is the trick. Because of locality, whatever you got here, so if this one is blue, after you measure that one, it follows, because these are space-like separated, that an instant before that one, I guess, giving yellow, this one was blue already, by locality. So if it's blue at t0, it's blue at t0 minus epsilon, because of locality, according to Einstein. OK, so we infer now that that one was blue even before this measurement was done. But the problem, of course, is that you could have measured another thing, say spin in the z direction versus spin in the x direction or whatever. And then you get green there, and then you get purple here. You apply the same reasoning, and you infer that this was purple just an instant before the measurement because of locality. But pink is not blue, so you are saying that this particle here was both blue and pink an instant before you measured the other thing. And so you're assigning two different wave functions, say spin up in z and whatever, spins x down in x, whatever it is, blue, purple, to the same physical state of the B particle. And that's the argument. Quantum mechanics is incomplete because you are assigning two different wave functions that have different predictions to one and the same ontic state, to one and the same real state of the other particle. So how do you deny this argument? You either have to reject locality, separability, or basically that's it. Or you say there is no external world, which some people have tried to say, but I mean, that's a very bad response because if there is no external world, don't take seriously any experiments, and then with what confirmation we have of quantum mechanics? None, because there is no external world, and experiments are in the external world. So the anti-realist move doesn't really work, so you better try to deny locality or separability. And here is the other trick that has been misunderstood in the literature. You don't have to do any experiments. This is a conceptual, even before you measure that, you already infer it has to be blue because of locality. So you didn't have to do the experiment. Before the measurement, it was blue already. That's kind of the point. So it's kind of clever also in that way. Anyway, you might ask, why do we even care about separability or locality or any of these things? So let me read this passage. It's a very important passage in the 1948 article by Einstein. Further, it appears to be essential for this arrangement of the things introduced in physics that at a specific time, these things claim an existence independent of one another, insofar as these things lie in different parts of space, B and A. Without such an assumption of the mutually independent existence of spatially distant things, an assumption which originates in everyday thought, physical thought in the sense familiar to us would not be possible, nor does one see how physical laws could be formulated and tested without such a clean separation. And then he goes on to talk about locality and how important locality is. But what Einstein is trying to say is, if you really take seriously that there are two objects, two entities separated in space, and these are physical things, you have to think they have some states, even if you don't know which states. Otherwise, you're saying they're physical things without physical states. So why are they physical things to begin with? That's kind of the upshot of what he's trying to say here. Okay. How to respond? You can reject locality, of course, or you can reject separability. Rejecting separability is too hard because if you reject separability, you cannot even formulate locality. Because to formulate locality, you have to say that the state of A cannot affect the state of B in a superluminal way. But to say that this has a state, and this has a state that cannot be affected, is to accept a separability. So to even formulate locality, you need separability. So the more, I guess, the less drastic move, which is still drastic, is to reject locality. This is the journal where Einstein published this paper, but notice a curious thing. First, it's a philosophy journal. It was created in 1948. Second, you have Bohr, Einstein, de Broglie, Heisenberg, Reichenbach, and Pauli, all publishing in this same issue. It's the same issue in this philosophy journal. This is not a coincidence. It was getting harder and harder for physicists, especially physicists interested in the foundations of quantum mechanics, to publish their work in philosophical, their more philosophical work or their more foundational work. So they had to find new spaces, like this journal. This journal, actually, the arguments here are maybe the most well-known arguments in these debates between Einstein, Bohr, Heisenberg, and others, but they had to do it in a philosophy journal. In fact, you know, Bell's paper of 1964, where he publishes the Bell inequalities, is published in this journal called Physics that nobody knew, and it lasted 3 years only, and then it disappeared. Extremely kind of obscure journal. Then most of the debates about the violation of the Bell inequalities are registered in this thing that is not even a journal. In the Q&A, I can talk more about that. I have a lot to say about that. But my point is, these physicists were desperate to find places to publish their more foundational interpretational things because physics journals were not accepting them. So Bell had to go to this obscure and new journal that disappeared 3 years afterwards. Okay, very briefly in the last 10 minutes or so, let me kind of finish up the story. So we have the incompleteness argument, and we have Einstein saying, you know, quantum mechanics is incomplete. Why? Well, first here is an argument, like a premise by premise argument, the thought experiment that I just gave. But second, he still thought that the most natural way of understanding the wave function is as capturing statistics of ensembles. He still thought that what these probabilities meant at the end of the day is like you prepare 100 ensembles and you get some frequency distributions and that's it. It's like an epistemic thing, similar to in statistical mechanics where you have probability densities and all that for the position of particles. So you may think, well, maybe there is a way of building a hidden variable theory. That is, a theory that complements the wave function with new variables that have more information about the physical state. Remember, if quantum mechanics is incomplete, there is more about the state of an atom than what the wave function says. So why don't you try to come up with a theory that has more variables, hidden variables as they're called, to describe those additional degrees of freedom that the wave function does not capture. Well, Einstein himself tried to do that and he couldn't. Then von Neumann in 1932 proved that you can never do that. If you come up with a model that has more variables, more information about the system, you will not recover the predictions of quantum mechanics. Okay, I can talk in the Q&A about this, but essentially the idea of these models is that you are trying to recover the predictions of quantum mechanics, but you are doing that through these lambdas, and you are doing like averages of these lambdas. So you assume that you just don't have enough information about the system, and if you do this like average of lambdas, you should be able, depending on the model, to recover the probabilities of the Born rule, but through the lambdas, right? So you get back quantum mechanics, but you get it by adding these hidden variables, the lambda variables. I can talk about this in the Q&A a bit more, but that's kind of the idea. Okay, let me just skip this. Now, okay, so 1932, von Neumann proved you cannot do that. I mean, I just show you like very quickly a mathematical model, but he said you cannot do it in a way to recover the predictions of quantum mechanics. But then in 1952, David Bohm published what we know now as Bohmian mechanics, which is similar to the Broglie quantum mechanics, but it has a bit more stuff on it. And it is a hidden variable theory, and it works. It has all the predictions of quantum mechanics, and it has two equations, so you have to add this one. This is an equation that tells you the velocity of the particles, how they change in time, and that's it. With those two equations, you get back all the predictions of quantum mechanics. What's interesting about this is non-local. The velocity of each particle depends on the position of everything in the universe at the same time, first. But the other interesting thing is that it solves the measurement problem. You don't have to do weird things about like the collapse by the observer or define what a measurement is. Forget about all of that. You don't need to do it. You can just do Bohmian mechanics and never solve the measurement problem. It doesn't emerge there. Everything is quantum, and that's it. The wave function for Bohm is like a field, but it's like a weird field because it has higher dimensions if you have more than one particle. So this is you probably have seen this. This is from a paper from, I think, 1979 of the trajectories of Bohmian particles. Particles in Bohmian mechanics always have positions and velocities all the time. They are like classical particles in that sense, always well-defined. The thing, though, is that it's very non-local, first, and second, the probabilities emerge because of uncertainty about the initial state. And we can never get full information about the initial state, and Bohm shows that those probabilities end up matching the probabilities of quantum mechanics. So the probabilities that you see in quantum mechanics, according to Bohm, are just a result of ignorance about the initial state of the particles with well-defined velocities and well-defined positions. But what about von Neumann's proof? He proved you cannot do that. Well, the proof had a mistake. And that mistake Bell showed in 1966, but actually a German mathematician, Grit Hermann, who was also a philosopher, and who unfortunately people have neglected for all this time, actually has shown in 1933 and 1935 that von Neumann proof didn't work. She was an interesting, I guess, character in the story because she was first a mathematician working under Emily Nether. She was very good at math, and as soon as she graduated, she said, I want to do philosophy. And she didn't find a job in math, she found a job in philosophy, and she started doing philosophy of quantum mechanics, and she corresponded with Schrödinger and Heisenberg and many others. Anyway, final part of the story. So let me stop for a moment here. So remember, Einstein was complaining quantum mechanics is not complete. And then people say, OK, go ahead and complete it. He couldn't complete it. Bohm did with his 1952 paper. Einstein didn't like his Bohm solution, actually. He thought it was too cheap. And things kind of stayed there, and people were like, OK, if it's complete, we don't know how to complete it. But we know we have to abandon locality or separability, because Einstein showed that. That's all we know, but we don't know what else to do. But the story is in the 40s and 50s when Einstein was old now, and people thought he was just kind of going a bit crazy and saying weird things, and his physics was, and he was just kind of lonely in the complaints about quantum mechanics. Well, that's not true. So let me just read you a couple of quotes of the founding fathers of quantum mechanics who in the 20s were extremely convinced that they have solved all problems and that Einstein was wrong. And now they are very different things. So here is Jordan. The notion of decision or quantum jump or some other concept not containing the Schrödinger equation is necessary and unavoidable. It is then apparent that the situation thought it is clear, it is then apparent that the situation does not allow a complete and final analysis. There remain open certain questions. It seems to me that entirely new conceptions are necessary. So he thought quantum mechanics in the 50s had many problems, mostly related to the measurement problem and other kinds of things like that. Here is Born. It would be silly and arrogant to deny any possibility of a return to determinism, like the kind of theory Einstein wanted. For no physical theory is final. New experiences might force us to alternatives and even revisions. I expect that our present theory, quantum mechanics, will be profoundly modified. But I should never expect that these difficulties could be solved by a return to classical concepts. I expect the opposite, that we shall have to sacrifice some current ideas and use more abstract methods. Here is Pauli. All of these figures in the 20s and 30s were very adamant that quantum mechanics is done and that Einstein is just wrong about complaining about these things. Here is Pauli. The question is never, will the present theory remain as it is or not? It is always, in what direction will it change? So he's saying, this quantum mechanics that we know is going to go at some point. Here is Rabi from the previous talk. Schrödinger was always unhappy about the whole thing, and I am too, to the very present day, in the sense that I can't get myself to regard quantum mechanic theories as other than provisional in some way. This was already in 1963. All these big figures in quantum mechanics saying, you know what, we do think there is much more to say about quantum mechanics. And here is Dirac, 1982, like many years after. It seems clear that the present quantum mechanics is not in its final form. Some further changes will be needed, just about as drastic as the changes made in passing from Bohr's orbit to quantum mechanics. It may very well be that the new quantum mechanics will have determinism in the way Einstein wanted. I think it is very likely, or at any rate quite possible, that in the long run, Einstein will turn out to be correct, even though for the time being, physicists have to accept the Bohr probability interpretation. Again, another founding father saying, you know what, maybe Einstein was right all this time. I'm almost done. This quote I like a lot. I start with an awful confession. This is by Leggett. If you were to watch me day by day, you would see me sitting at my desk solving Schrödinger's equation and calculating Green's functions and cross-sections exactly like my colleagues, like all of you. But occasionally at night, when the full moon is bright, I do what in the physics community is the intellectual equivalent of turning into a werewolf. I question whether quantum mechanics is the complete and ultimate truth about the physical universe. Last slide. It's impossible to say, what happens afterwards, but very, very briefly, Bell publishes the 1964 inequalities, right? Then you do the first experiments in 1969 and 1972 with Closure, Shimoni. I always forget, it's like the CH inequality, Horn. Anyway, the version of Bell inequality that you can actually test in an experiment, taking into account errors and all of that. You do that in the early 1970s. And then, very interestingly, a whole industry starts there, of an industry of trying to figure out ways of making these experiments with entangled systems in a way that you have specially space-like measurements. So when you measure something here, no light signal can arrive to this thing. It's very hard to do that. I'm not an experimentalist, but you have to figure out ways of being very fast. And at that point, the technology was not there. So in trying to test the Bell inequalities, a new era of quantum mechanics emerged, a new, more applied era where physicists were trying to figure out ways of testing these things and testing these correlations and this kind of thing. And that era eventually led to Seilinger, Aspect, and Closer winning the Nobel Prize in 2022, all because of Bell trying to figure out if there was a way of putting into experiments Einstein's incompleteness argument. And let me just end. Okay. These are the Closer, Shimoni, Horn, Holt. Last quote of the day. Einstein, 1944. So many people today, and even professional scientists, seem to me like someone who has seen thousands of trees, but has never seen a forest. A knowledge of the historic and philosophical background gives that kind of independence from prejudices of his generation, from which most scientists are suffering. This independence created by philosophical insight is, in my opinion, the mark of distinction between a mere artisan or specialist and a real seeker after truth. Then 1955, Einstein dies, and curiously, if you look at the desk when he died, the last journal he was reading was a philosophy journal there in the corner. That's the picture that he was taking the day after he died. And that's it. Thanks.
We can still do Q&A, but if you are needing a ride back to the hotel, it is leaving in like 3 minutes, so grab a lunch and hop on. If you're going on the Burke tours or you have other transportation, then don't worry about it. Sit tight and enjoy some Q&A. All right, I'll hand it back to you.
Thank you. So any questions? Yes.
Thank you for the wonderful talk. It's kind of very unique. This is my first time attending a history lecture of quantum mechanics. My question is like, or maybe I need more clarification on the Einstein's incompleteness argument that locality and separability imply that you can assign two wave functions to the same like object, right?
Yes.
So, and then you later said that maybe by adding like more hidden variables, you can solve this problem of incompleteness. And that's what Einstein was thinking about. How can this happen by adding more degrees of, like more description to the system that you can resolve the incompleteness argument? Thank you.
Yeah. Oh, I don't need it. Okay. I have my own microphone here. Good question. So notice that what we say now is that locality is violated in these experiments, like in the. Now, you don't have information, so you cannot transmit information faster than light. But that's not really locality, at least not how Einstein thought of it. He thought like, if you change the state here, and that change of state here does change the state here, even if you don't know it. No humans. If there are humans or not, it doesn't matter. If you change the state here, and that immediately changes the state there, that's a violation of locality in his definition. So what happens now is that when I say you can add more variables, like really what's going on is if you add more variables, you still have to obey the argument, right? The argument is the argument, but then you have to violate a premise. And the premise that people say it's violated is locality. So for example, Bohm explicitly recognizes this, and his theory is super non-local, but it still respects the no signaling theorem. So it's non-local, but you cannot exploit that non-locality in any way to gain any advantages. Does that help or not?
So, is it local or not?
No.
But you said like you cannot transmit information faster than light.
Yeah, because that's not the definition of locality that they are using. So if by locality you mean you cannot transmit information faster than light, it is local. If by locality you mean that there is a state here, and changing that state cannot change this other state, forget about information. It's a matter about the external world now. If you cannot do those changes like that, I mean, if by changing this you change that instantaneously, it's non-local in the sense of Einstein. Does that make sense? So there is locality in the sense of information, and there is locality in a more kind of objective, non-information sense.
Okay, and it's the second one that appears in the argument. Thank you.
Yes.
And yeah.
So about the Bell test, there's this interesting fact about you need to change the basis randomly. So if you're measuring say sigma z or sigma x, you have to do random choices on the basis to extract the classical probabilities, right?
Yeah.
And one of the arguments there that in experiments you need to have essentially certifiable random numbers to be able to rotate the basis to do the test. Otherwise, it still doesn't prove that your Bell inequalities basically work because you have correlations in the random numbers that you're creating.
Yes.
So one thing about that, and second thing is the measurement postulate is still there. We don't know why it works. It's just a postulate, right? Nothing is resulting in that regard anyway. So, yeah,
thanks. Yes, let me start with the second one first. So if you ask people working on the foundations of quantum mechanics, and some of them are mathematical physicists, some of them are actually philosophers of physics, they will say that you have theories where the postulate, what you call the measurement postulate, sure, it's there, but it's not primitive. So for example, in Bohmian mechanics, you derive it. So you don't put it by hand. You kind of derive it from the other equations, right? In standard quantum mechanics, like the textbook version, it is a postulate. And von Neumann was very worried about that, and he was trying to figure out if there is a way to say when it's what's a measurement and what kind of processes involve measurement to apply the postulate. Because the question is, sure, it's a postulate, but when do we use it? If an electron interacts with another electron, you get superposition. But how many electrons you have to, like, at what point, like, you say, okay, this is a big system, and now, like, now you get the collapse of the wave function, right? And that kind of worried them a lot. But sure, it's a postulate. In Bohmian mechanics, it's not. And in many words that I didn't have time to talk about, it's a good question how to understand the Born postulate, because nothing collapses. You just have branching, right? You branch and branch and branch forever. And the postulate just tells you the distribution of outcomes. If you're like a god that could see all these branches outside the universe, these probabilities will correspond according to them to frequencies of measurements of copies of you and things like that. The first question, that's a very good question. So, I mean, it's connected to what's called the free will assumption as well. Like, as an experimentalist, you have to choose what to measure at some point. And then the question is the choice of the experimentalist in some way partially correlated with the state, the ontic state of the system before the measurement? If it is, you don't have Bell's theorem does not go through, like the inequalities do not go through. And there were physicists trying to compute how much free will you can have to still preserve certain inequalities. And so they were kind of finding maximums or minimums of how much independence there could be between the ontic state of you as the experimentalist and the ontic state of the system. But that's still an ongoing, I guess, debate. And like whether or not you have true random generators itself it depends on what interpretation of quantum mechanics you have, right? Bohm said, no, there is no true random generators at all. It's just uncertainty in the initial state. And if you go back to the beginning of the universe, uncertainty in the initial state there about the positions. But for all practical purposes, it does not matter because we cannot access that information. And so we have effective randomness, I guess. Does that help? Yeah. Thanks.
What's the problem with the pilot wave theory with Bohmian mechanics? There should be some problem that people don't.
One of the problems people keep citing is that it's very hard to make relativistic, like to integrate with quantum field theory. People have tried to do that, but it's extremely hard to do that. I mean, it's very non-local to begin with, and there have been modifications, but that's really the main problem. The other problem people sometimes cite is that they think it's kind of like cumbersome to use because of the second equation, the guiding wave equation. But that's more like how convenient it is than maybe a philosophical problem with the theory. The main one is the relativistic thing, I would say.
Great. Any other questions? Okay, if not, then I'm so sorry. Sure.
I wanted to ask, what was like Minkowski's reaction of quantum mechanics? Because I know he had like a problem with Einstein, although he was his teacher. Like, did he really accept the notion of quantum mechanics when it came up?
I mean, I have to confess, I don't remember when he died, but I would imagine that he didn't live for much of the period where this thing, I mean, yeah, I would have to check when Minkowski died, but I suspect he was not involved in these debates. He was older by then, and maybe he even died before. I mean, you can check, I don't know when he died, but he was not part of the story. So either he died before, or he was very old at that point, and he was not interacting with them, yeah.
I know he was contesting the notion of special relativity.
Yeah, but that was in 1908. So when Einstein, that was like in the beginnings of the 20th century with Einstein, yeah.
Great, thank you. Okay, so with that, that's the end of the talks for today, for the last day of the summer school. You can please help yourself to lunch, and at 1:30, we'll be having the tour of Berk, so we'll get more information on that. Thank you.
Yeah, just some quick closing announcements. For the students and postdocs in attendance, we will probably be sending out a survey to you guys in the next couple of weeks so we can hear your feedback on the school and help us to improve for the coming years. As Vea mentioned, there is lunch out here for you guys to pick up and eat. Can I just get a show of hands on who's planning to go on the lab tours? Okay, a few. There should be someone here that can escort you up to Burke after lunch. Is there someone from Vlad or Sasha's group who can do that? We'll find somebody. And then the tours will start around 1:30 up there. Other than that, thank you so much for attending, for your attention this week. We greatly appreciate it. So thanks all for being here. Take care.